respected invited guests of this inaugural function, respected resource persons of this FDP, dear participants, and my dear fellow organizing committee members, good morning to one and all. Recent advances in earthquake engineering is one of the hot subjects for research scholars, academicians, practicing engineers, and students. There are many more areas there to explore in the field of earthquake resistant design because of the uncertainties of the external force, that is earthquake. We have received an opportunity to organize this faculty development program under the sponsored scheme of AICTE Training and Learning, ATAL. The total FDP is divided into 14 technical sessions of 2 hours each. There will be 3 such sessions per day. The FDP is organized for 5 days starting from today. Today, we are fortunate to have our chief guest, Dr. E.J. James, member of governing body, Wetland International South Asia, and former executive director of Center for Water Resources Development and Management, CWRDM, Calicut. The details of the chief guest will be shared soon. On behalf of organizing committee, let me welcome you, sir, for this function. Dr. Saji CB, our principal and the president of this function, is a constant motivator for all the activities of this campus. Welcome you, sir, for this function. Dr. Sudha Balagopalan, Dean Academics, Dr. Krishnachandran, Vice Principal of Vidya, gave us all the guidelines based on their previous experience such programs. With gratitude, welcome you, sir and madam, to this function. Our respected resource persons are Dr. Katta Rengatramana, Dr. KBM Nambudirippar, Dr. Ajay C, Dr. TP Somasundaran, Dr. Ajit A.S., Dr. Robin Davis, Dr. Syed Jalaluddin Shah, Dr. Bharati Raja, Dr. Rohan Bhaskar, Dr. Kavita P.E., Dr. Deepa Balakrishnan, Dr. Smita K.K., and Professor Anil Kumar. All of them are experts in their own area, and they are going to share their ideas as well as their experiences in the coming FDPs. I hope all of you will be benefited from, and we can explore their potential in their expected areas. On behalf of organizing committee, welcome you all for this function. AICT official members, Vidya International Charitable Trust members, those who are joined in this function, then my fellow heads of departments, faculty members and staff members of Vidya, the parents of our students, welcome you all for this function. Dr. Abhilasha, the co-coordinator of this program, is actually the backbone of this FDP. Starting from the forwarding the application form for the approval from AICT, organizing the entire program, her contribution along with our team members, Ms. Nisha, Ms. Ardra, Ms. Ampili, and Mr. Kiran, made this program to a reality. Let me officially welcome you all for this function. Last but not least, our respected invited participants of around 100 members from different parts of India, without which this program will not run. I know all of you are eagerly waiting for the upcoming technical sessions and hope it will be benefited for you for your future activities. Welcome you all for this function. Wishing you all the best and welcome you once again. Let me conclude. Thank you.
Thank you, sir, for the welcome address. Next, I would like to invite Dr. Saji CB, Principal of our institution, Vidya Academy of Science and Technology, Thrissur, for the presidential address. Sir, please.
Thank you, Dr. Abhilasha. Chief guest of the day, Dr. A.J. James, Pro Vice Chancellor, RNC, California University, our Dean Academics, Vice Principal, Head of the Department, Civil Engineering, Co-Coordinator Dr. Abhilasha, members from the Trust, officials, heads of various departments, dear delegates from Vidya as well as various other institutions, a very warm good morning to all of you. At the outset, let me also extend a very warm welcome to every member who have joined us in the inaugural function of the Faculty Development Program, Recent Advances in Earthquake Engineering. Vidya as a philosophy, our philosophy has been empowerment through education. We strongly believe knowledge is power, and knowledge is the leading force for progress, and knowledge is acquired only through education. Hence, in our vision itself, we said progress through education. We are committed to the society, educating them with the latest. We educate ourselves. We educate the general public as well. Faculty developments programs like this quite frequently has been organized by Vidya to make sure that we update ourselves and the co-fraternity of teachers so that the right knowledge can be transferred to the younger generation and we can be part of progress of the country. Let me thank the All India Council for Technical Education for sanctioning the program to us. Many of you are aware, and I think there are few who may not be, it's the first time we are interacting with the Academy of Science and Technology. We as an institution has been established in the year 2003 under Vidya International Charitable Trust. This trust is a fully charitable trust formed by NRIs, completely NRIs. Currently, we have a strength of 1,200 plus non-resident Indians managing the trust with full commitment to the society without expecting anything in return. The campus is situated in more than 30 acres in a very serene and beautiful campus. Probably many of you may be knowing, we also have the largest Nakshatravanam for the star forest in our campus. The campus have programs, undergraduate programs in civil engineering, computer science, electronics, electrical, mechanical, production. And we also have the master's program in civil, electronics, electrical, as well as Master of Computer Applications. The Civil Engineering Department, who is the host department for this program, is also accredited by the National Board of Accreditation. And we have more than 2,700 students in the campus at a time. The topic for discussion today, as rightly said by Dr. Justin Jose, is one of the most relevant topics. Natural calamities are a threat to all of us. Mankind has faced many of the devastating earthquakes, one among the largest being in 1556, the Shaanxi earthquake in China, which has killed more than 830,000 human beings. One of the biggest challenges, as I understand, in this is we are unable to predict when an earthquake is going to happen or how strong it is going to happen much in advance. Though we have scientists and technocrats, technologists has been able to rightly predict, at least with good accuracy, we are able to predict cyclones, floods, maybe depression at the sea, etc., etc. But as far as prediction for earthquake is concerned, we are still miles to go. What currently, therefore, the community of scientists and engineers and faculty members like us are more involved is in life-saving designs, how to protect our buildings, how to protect our infrastructure and human life if an earthquake happens. So I'm sure with the kind of intellectuals available today during the program, we'll be able to strongly deliberate on various issues, various aspects of earthquake engineering, and we'll come out with at least some fruitful thoughts, research in this direction, which will be highly beneficial to the society and to mankind as well. What do we expect, in fact, from this? We expect good networking among all of you, all the delegates who are joining here. Deliberate what is happening, what are the recent advancements, and what are the possibilities and challenges in earthquake engineering. Hopefully, in due course, in future, this community will be able to come out with an accurate method to prediction, methodology to predict earthquake. If we are able to do this at any point of time, I think a Nobel Prize is there for us. It is such big contribution. It would be such big contribution to the scientific world that if you're able to rightly predict. So let this 5 days of interactions be highly beneficial to this topic of discussion. And I thank all the experts, starting from Dr. E.J. James, who has been good enough to join us to inaugurate the function. Thank you so much. And I also once again welcome all the participants, delegates, as well as the resource persons to the function, to the program. And let me wish all the very best to all of you. Thank you so much.
Thank you very much, sir, for your motivating words. Now let me share my screen. Now, it is time, the auspicious moment to invite our chief guest, Dr. E.J. James, to this virtual gathering. Can you see the screen? Sir, are you able to see the screen?
Sure.
Okay, thank you, sir. Okay, so Dr. E.J. James is Professor Emeritus and Director, Research and Consulting at Carney University, Coimbatore, Tamil Nadu. He's presently the Professor Emeritus and Director of Carney University and a renowned wetland hydrologist. He's graduated in civil engineering from NIT, Karnataka, and also he completed his MTech in cosmic engineering from the same institute. He did his PhD from Calcutta University and carried out his postdoctoral work at the Institute of Hydrology, Welford, UK. He worked as scientist for 30 years in the Center for Water Resources Development and Management, CWRDM, at Calicut, and retired as Scientist G and Executive Director of CWRDM and the Director of Irrigation Management Training Institute of Kerala. Since 2008, he has been working in Carney University, Coimbatore in different capacities as Director, Water Institute, Director, School of Civil Engineering, Director, Interdisciplinary Research, Dean Research, Dean, School of Agriculture and Biosciences, Pro Vice Chancellor and Vice Chancellor. He carried out more than 80 funded research projects for national and international agencies and has more than 150 publications to his credit. He served as consultant to several agencies such as the World Bank, UNDP, UNEP, GICA, and India-Canada Environmental Facility. He is chairman of Research Council of CWRDM and chairman of the Steering Committee for Publication of National Wetland Atlas of Ministry of Environment, Forest and Climate Change and Space Application Center. He is a former member of the Working Group on Tidal Waters of the International Commission on Irrigation and Drainage, and also member of the Central Wetland Regulatory Authority of Government of India. Sir is currently a member of the Central Water Commission's Research Committee on Surface Water. Sir has also served in several commissions and committees constituted by the High Court and Supreme Court of India. Dr. E.J. James is the recipient of Himalayas Award of the Institution of Engineers and several certificates of merit. Recently, the Tamil Nadu Agriculture University conferred on him the award of Distinguished Scientist. I know Dr. E.J. James personally and is very driving force and fun-loving and a motivational personality too. We welcome you, sir, to this event. May I now take this opportunity to request sir to inaugurate our FDP and address the gathering. Welcome, sir.
Thank you, Dr. Abhilasha. Respected Principal of Vidya Academy, Professor Saji, learned experts and resource persons, organizers of the FDP, and faculty members of different institutions. I consider it as a great honor to be in your midst today to inaugurate the FDP on recent advances in earthquake engineering, sponsored by AICT under its ATAL program. I am thankful to the organizers, especially Dr. Justin Jose and Dr. P.S. Abhilasha, who happens to be the alumnus of Karunya. Now, when you look at the earthquakes, where did this research on seismicity and earthquakes start? Way back in 1755, on November 1st, there was a great Lisbon earthquake. This great Lisbon earthquake killed almost, they say that the exact figures are not available, about 10,000 people. And the epicenter, which was just 200 kilometers from Portugal, developed into a tsunami and then killed more people in not only Europe, but also in Northwest Africa. And the great ambitions of the Portuguese to colonize the whole of Asia and Pacific and Africa came to an end with this earthquake. And this is an occasion on which people started doing research on seismicity and earthquake engineering. Now, the greatest earthquake which we have seen in this century perhaps might have been the 1960 earthquake of Bio in Chile, with a magnitude of 9.5 moment magnitude scale, which was formed about 200 kilometers away from the Chile coast in the Pacific. And it killed several people. The accounts are not known, made about 2 million people houseless, generating a tsunami of the height of about 7-story building, 25 meters. And it propagated to Hawaii, killed about 200 people there, and destroyed many houses. It traveled 2,500 kilometers to Hawaii within a period of 15 hours. And finally, it reached Japan, killed 138 people, and made about 1 million people houseless. Further, it propagated to Philippines and killed several people there. So when we talk about earthquakes, we will have to also think of the consequences of earthquakes and the safety to life and destruction of property. With this, we come to my topic. You can go to the next slide. What are the major areas of earthquake studies, if you ask me? Tectonic environments and structures of the earth, especially seismogenic fault zones. Please remember, when the earth was formed 4.5 billion years ago, there was no plates, and there was no need for plate tectonics. Long and short-term behavior of fault zones is something which are being investigated. Laboratory, field, and numerical experiments on the physical process of earthquakes. Primary and secondary hazards associated with earthquakes, and forecasting and mitigation of seismic hazards. These are all the areas which are gaining momentum in earthquake studies. Major disciplines involved are geology, seismology, geodesy, physics, and computer science. Now, let us have a look at what is earthquake engineering. We go to the next slide. What is earthquake engineering? Earthquake engineering, if you ask me, is a subdivision of structural engineering that focuses on designing structures capable of withstanding the immense levels of stress caused by seismic forces. As you know, that the Roorkee School of IIT Roorkee, at that time it was Roorkee University and Roorkee Engineering College, Jay Krishna and his dad started the earthquake engineering studies in an intensive manner in the country, knowing that some of the Himalayan regions are prone to severe earthquakes. Now, civil engineers specializing in this field usually work in geographic areas that frequently experience earthquakes, allowing them to test new technologies in real-world earthquake scenarios. As the science behind earthquake engineering is constantly advancing, the current engineering professions can benefit from examining a few of the innovations introduced to the industry. You may ask me why a water resources engineer should speak on earthquake engineering. You know that I have been really bothered about natural disasters, as the principal was telling. And I remember I came to speak on natural disasters caused by water at Vidya Academy a few decades back when Dr. Balakrishnan Nampia was the principal. So at that time, perhaps there was no Nakshatra garden there, but now they say that there is a Nakshatra garden. I want to see the Zodiac garden next time when I get an opportunity.
Yes, sir. You're warm welcome.
The 7 principles in earthquake engineering, as stated by Vision 2020 for the US, states that metrics to quantify resilience, tools for hazard awareness and risk communication, reducing the risk posed by existing structures and infrastructure facilities, developing and implementing new materials, elements, monitoring and assessing resilience, means to simulate resilience of systems, implementation and technology transfer. These form Vision 2020 for the United States in the area of seismology and earthquake engineering. We go to the next slide. Now, if you ask me, fundamental knowledge and enabling technologies will have to grow in earthquake engineering. Earthquakes cannot be prevented, but their global impacts on life, property, and economy can be managed. How can it be managed by engineers? This is a question which we are going to deliberate today in this FDP. Our civil engineering structure has to integrate sensor networks, intelligent controls, smart materials, and real-time health and condition monitoring. Now, we have been talking about, especially engineering colleges and students, about artificial intelligence, IoT, sensors, and all that. Industry 4.0. How can this be useful in the context of earthquake engineering is something which we'll have to look at. This trend will intensify and improve the efficiency and performance of these systems. Additionally, research to demonstrate the cost effectiveness of performance. We cannot go for any level of risk. We will have to decide on the performance level. Based on design practices, applications of new materials to reduce earthquake impacts, and improved retrofit strategies to facilitate removal of existing barriers to their adoption. Please remember, apart from Industry 4.0 technologies, we are also having a lot of things being built up, a lot of things being developed by civil engineers in the form of materials, in the form of techniques of construction, etc. These will have to also support earthquake engineering. Demonstrating that investments in earthquake safety, this is something which we have to tell the government while making the policy. The losses which we incur due to an earthquake is considerable. The principal was talking about the earthquake in China, how many people lost their lives. If we can avoid this by spending some money as a precautionary measure against this natural hazard, then it will be good. Moreover, various disciplines within earthquake engineering must work together. Let us understand that earthquake engineering is not a single mono discipline. It is an interdisciplinary study where a lot of other fields are involved. We go to the next slide. Yeah. Now, let us have a look at earthquake resistant design of structures, a multidisciplinary area with exciting developments in future. Most notable among these technologies are a complete probability analysis and design approach. It should be performance-based. What do you want? You want immediate occupancy, or do you want life safety, or do you want collapse prevention? You'll have to decide the level. Multiple annual probability hazard maps for response spectral accelerations, peak ground acceleration, with a better characterization of site soils, topography, near field effects. This is a field which is growing, and there is an immediate necessity to go in form the hazard maps prepared and revisited every year. Structural systems and devices using non-traditional civil engineering materials and techniques. We should not stick on to our traditional civil engineering materials. We can also look into it, but that should not be the only focus. New refined analytical tools for reliable prediction of structural response, including non-linearity, strength and stiffness degradation due to cyclic loads, geometry effects, and more importantly, effects of soil structure interaction. We go to the next. If you look at it, there are two terms you should understand with regard to the seismicity and structural interventions. First term is called seismic demand. What is the intensity of the earthquake and what is the demand? So first is seismic demand. Second is computed capacity. How much should be the capacity of our buildings, of our infrastructure, of our environment to combat this seismic demand? If you look at your left, you've got two curves there. You see on the left-hand side, you've got the predicted maximum demand curve. And on the right-hand side, you have got the computed minimum capacity curve. Now, please remember, there are limitations for this computational techniques. There are limitations in construction. There are limitations in planning. All these may cause a dark area, overlapping area between the two curves, the black region. So, in spite of the fact that we have computed the demand, and in spite of the fact that we have taken precautionary measures for capacity, there are still gray areas which we are not sure of. We come to the right-hand side, where we have got the interrelationship between seismic demand and structural capacity as applied to earthquake risk design. So in this, on the left-hand side, you've got the design earthquake. A design earthquake is affected by, it can be supported by hazard maps, local site effects, near surface and rupture directivity effects, spatial variations, topography effects, vertical motions, energy and duration of shaking. These are factors affecting the design earthquake. Now from that, if you look at the design code process, how this design earthquake is going to help it, you have a look at the center portion of that, the hazard characterization. In hazard characterization, it depends on the design earthquake. Performance levels will have to be fixed. Performance levels can be the immediate occupancy, it can be life safety, it can be collapse prevention depending on the levels. From that, we come down and we come to the performance objectives and performance requirements and risk which we can take. And it has to be, all these will have to be verified by actual performance and analytical methods and lab testing, experimental and perspective course, which we'll have to develop. Now, to achieve these performance objectives, our job as structural engineers is to find out the structural system for seismic response reduction. Come to the right, extreme right. Structural system for seismic response. What can we do as engineers? Reducing seismic forces, enhancing damping, adjusting structural properties, These are the strategies which we can follow. And for these strategies, what are the techniques to be followed? Phase isolation, energy dissipation devices, structural control systems. Our work is mainly that. We have got a set of strategies as earthquake engineers, and we have got a set of techniques. And this interrelationship should be kept in your mind while going in for design. We go to the next slide. Now, if you look at it, there are two parameters which you have to think of. Global displacement capacities for various performance levels. This is a very big question which we'll have to tackle. On the top, you got seismic hazard levels, probability of occurrence or exceedance in 50 years. Probability of exceedance in 15 years. On the top, you got the global displacement, which is called DD. And at the bottom, you got displacement capacity, global displacement capacity DC, which means DC by DD, if it is 1, we have to be safe. Okay, now have a look at it. Our performance levels, 1 is immediate occupancy. If you want to have 10% exceedance, you got 1 at the bottom. On the left-hand curve, 1 at the bottom. It's immediate occupancy. 2, life safety. You have got 2 at the bottom of the X. You see the horizontals. 2 is horizontal scale on the left-hand figure. That is 2, which is life safety. And you've got 3, collapse prevention. So if you got a curve like this, you can have an idea. And you can also have an idea about what is needed for total containment of the situation. But please remember, we are talking about something not predictable. So that is something which you have to keep in your mind. Next slide. Now on the left-hand side, you got all the 3 cases. Left-hand side curve, you see, you got first one is occupancy, immediate occupancy. Second one is, as I have said, life safety. Third one, you see, it is not designed up to that. It breaks. This is the global capacity curve from non-linear static procedures. So on the x-axis, you have got on the left-hand side displacement DC, and on the vertical axis, you have got the global force. Now from that, let us come to the right-hand side. This is the performance level with regard to one element, only one element I'm talking about, one specific performance level, say life safety. You've got design alternative A. You've got chances of 20% of exceedance in 50 years. If you go for design alternate A. If you go for design alternate B, we can have much better life safety system. 2% chance of exceedance in 50 years, somewhere near 2%. So this is something which we'll have to keep in our mind when how much is the risk which we can take when we go for our structures. Next one. Now we have got the historical traditional approaches and the modern approaches for this. What was the historical approach in earthquake design, if you ask me? You got the figure on the left top. Design seismic forces were assumed proportional to structure's mass and typically verified between 5 to 10% of the mass. linear design is used with appropriate factors of safety to account for uncertainty in seismic demand and capacity. If you think of the Idiki Dam or talked about Mullaperiyar Dam, we always say that the structure's mass prevents its collapse. This is a traditional method of design, a historical method of design. Now we come to the traditional code, bottom, figure bottom on left. Design seismic forces for linear design are obtained by reducing elastic demand by a factor R. We will have to reduce it by a factor R, which varies based on typical inelastic response of spectral demand. So it is directly dependent on the typical inelastic response of structure. Depending on that, we will have to come to the factor R. The reduction is justified by expected ductility, overstrength, and redundancy. So this is the traditional code. Now we go to the next. Now you have got to the future trend. Here we come to the spectral acceleration. If you think of, and you have got the reduction of demand for an elastic capacity of structure, we will read out the theory on the right-hand side. Inelastic seismic demand is based on inelastic capacity of structure. Okay? Both seismic demand and capacity of structure are inelastic. As inelastic displacements increase, the period of structure lengthens, damping increases, and demand reduces. If you look at it, the figure on the left-hand side, see the reduction of demand for inelastic capacity of structure. If it is coming down. And you've got a point there, which is called the performance point. And you've got the capacity curve and you've got the performance point. So that's what we meant by the capacity, as inelastic displacements increase, the period of structure lengthens, damping increases, and demand reduces. The capacity spectrum method generates performance point where displacement is consistent with the implied damping. As I have said, the performance point on the left hand, which implies a unique damage stage related to a specific Husserl level. So this is the future trend. We will have a clear-cut idea about the performance point, and we can design for that. This is adapted from ATC 40. Next. Now, when we are talking about ground motions, you know that this is not a perfected field. More is required, more knowledge is required to have a clear-cut idea and zoning. Ground motions modified by underlying alluvium deposits and ground features can have an effect on the impact on the structures. Now we have got a few cases which are illustrated here. The fault zone is there, it goes and then impinges upon the structures. It varies. But there is one thing which I want to say. In spatial variation, where like a bridge structure, we don't consider any one of these parameters. Next one. Now, this is something which we'll have to consider. Factors contributing to spatial variation of ground motion for extended structures. Now, as I have said that in extended structures, we are not much bothering about the ground motion directly in the design. Now you've got a first case there where the wavefront is moving out The second one, there is an attenuation because of the fault source. And at the bottom, we have got different sources, a source A and source B, which is moving towards the base of the foundation of the structure. And on the extreme right, left, right, bottom, you've got a scatter. And see from the source A, the waves scatter. And what happens, you can see that when they impinge and they reflect, what will happen to this structure. These things are not very clearly understood today, but as the science grows, we may be able to have much more clarity on this. We go to the next. Now, major techniques for structural response control during earthquakes is fixed base systems. These are conventional structures absorb seismic energy through inelastic deformations in structural members. Large inter-story drifts cause structural and non-structural damage. However, loss of life and collapse is prevented. You go to the right-hand side, B, seismic isolation systems. Structures are supported on isolators. You see the isolators, which decouple structures from damaging earthquake components and absorb seismic energy, adding substantial damping. You go to C, energy dissipation systems. Energy dissipation devices absorb seismic energy, thereby reducing the demand on primary structural members. Primary structural members are saved by that. Structural and non-structural damage is significantly reduced. We go to the fourth case, bottom right-hand side, active control systems. Lateral strength, stiffness, and dynamic properties of the structures are adjusted during the earthquake to control its response. Complex control mechanisms and elaborate hardware is required for this system. We go to the next. Now, a few of the innovations introduced in industry are bearings. Lead rubber bearings comprise of a lead core set within a rubber housing, which is then encased between two thick steel plates and fixed at the base of a building's foundation. This is available in the market. Steel plate shear walls. These walls are designed to limit lateral force in buildings by using steel shear walls that absorb stress and bend, but do not entirely buckle under pressure. These walls are also significantly thinner than concrete shear walls. Controlled rocking. These high-performance systems utilize brazed steel frames that have elastic properties. This allows the steel frames to rock upon their foundation when an earthquake happens. Tuned mass dampers. To create a mass damper, large metal pendulums are suspended and attached to cables at the top of the tall building. These pendulums act as an inertial counterweight. It moves and keeps the building as centered as possible when an earthquake occurs. Seismic cloaking, which is a new field, described as a completely new approach to earthquake resistance. Seismic clocks are currently being tested as a means of creating protective barriers capable of rerouting seismic energy away from above ground structures. Dampener. Seismic cloaking involves the modification of soil and other ground materials surrounding a building to deflect or redirect the force created by an earthquake. These are some of the materials available in the market. We go to the next. Go to the next. We have time up. in future, earthquake risk design of structures is most likely to witness the following significant development. One is a complete probabilistic analysis and design approach that rationally accounts for uncertainties of the structural design. Structural system to gradually replace deterministic approaches, especially in characterization of the loading moment. Performance-based design process to take center stage, making conventional descriptive codes obsolete. We should know what is the risk which we can take. And we'll have to design, because cost effectiveness is very important for a design for a civil engineer, apart from its strength. Acceptable risk criterion for design purposes to prescribe the performance objectives and hazard levels. Multiple annual probability maps for response spectral acceleration. Development of new structural systems and devices will continue for phase isolation, passive energy dissipation, and active control systems. Along the proliferation of non-traditional engineering materials. Analytical tools for reliable prediction of structural response. We are having of new tools. Tools and performance-based design process will continue to improve and be updated to include new devices and materials. Area of soil structure interaction. The least understood aspect in the field of earthquake engineering is poised to witness the emergence of new numerical techniques to model non-linear soils and structures. Next one. Now, it is fairly well accepted that earthquakes will continue to occur and cause disasters if we engineers are not prepared. Assessing the earthquake risk and improving engineering strategies to mitigate damages are the only options before us. And you are the people to do that. Geologists, seismologists, and engineers are continuing their efforts to meet the requirements of improved zoning maps, reliable databases of earthquake processes and their effects, better understanding of site characteristics and development of earthquake risk designs are needed. As for the engineer, the ultimate goal will remain the same, to design the perfect but cost-effective structure that behaves in a predictable and acceptable manner. The ongoing research and development activities in the area of EQRD of structures offer significant promise in realizing that goal in the coming years. Next one. Now, I thought that I was looking at the earthquakes which had happened. I found that more people are killed not because of earthquake, but because of the tsunami which followed intensive earthquakes. If you look at it, this is the word tsunami written in Japanese on the left-hand side. Tsunami means a harbor wave. You see the two types of earthquake possibilities in the bottom of the sea. You've got the strike-slip size type, which may not create a tsunami under normal circumstances. But on the right-hand side, you've got the dip-slip fault, which will definitely, if the magnitude is very high, create tsunami waves. Shallow focus earthquakes of strike-slip and dip-slip. Now, as you know that I have studied marine structures in Surathkal for quite some time, and I thought that I will give you some idea about this also. Our Kata is here. I don't know whether Kata knew that I studied marine structures. We go to the next. The magnitude of tsunami-genic earthquake, if you want, lower limit of earthquake magnitude of tsunami-genic earthquake is M is equal to 6.3 plus 0.55005 df. where M is the magnitude of the earthquake in Richter scale and D of the focal depth in kilometer of the epicenter. The Richter scale may be expressed in terms of energy of earthquake. M is equal to log E minus 11.8 by 1.5, where E is energy in ergs. Next one. Potential energy of the uplifted water. Potential energy of the uplifted water can be calculated if you know the energy in ergs, density of seawater, acceleration due to gravity, total area of uplifting, and average value of the square of the uplifted heights of water. Next one. Have a look at it. When one plate goes underneath the other, what happens? This is the formation of tsunami. So please remember, in Chile, the Indonesia plate subducted under the South American plate, and it created a tsunami of the height of a 7-story building. When it traveled 2,000 kilometers and reached Hawaii, it was just a 3-story building height. Please remember how it travels. Next one. Next slide. Yeah, height of tsunami near source of generation is log 10h, 0.75 m minus 5.07, where h is the height in meters and m is the Richter magnitude. Period t in minutes of the primary tsunami is log base t is equal to 0.625 m minus 3.31. When a bay or harbor is very long in relation to the tsunami wavelength, the tsunami may cause resonance if the natural mode of oscillation of a bay or harbor corresponds to the period of the tsunami. The damage will be considerably more. Next one. Yeah, you see the long period waves. 1, 2, 3, long period waves on the top. That is a type of waves which we have got long periods and very long wavelength. This is what we find in the tsunami waves. Next one. Now, this is an illustration of the American. Here, what you find is that when depth is 7,000 meters, the tsunami waves can have a velocity of about 943 kilometers per hour and a wavelength of 282 kilometers. See how it travels fast and how the height of the wave diminishes by coming to the coastline. Okay, next one. Now, this is the one I was talking about in Chile, 1960. What happens is that, see the distance from Chile to Japan. And in Japan, 138 people died and about 1 million people lost their houses. See the distance traveled by it in 25 hours. Just within 25 hours, it reached the Japanese coast, traveling to the Pacific. Next one. Next one. Yeah, you've got a seismograph there. You've got a seismograph at Sumatra just before the 2004 tsunami. Next one. Next one. Yeah, you've got the tidal gauge readings in Sumatra during the time of the Great Earthquake and the tsunami of 2004. Next one. Now, some of the observations based by the team sponsored by American Society of Civil Engineers based on 2004 tsunami at Thailand, Sri Lanka, and India. You can go to the next one. You go to the next one. Next one, next one, next one. Yeah. Now, you can have an empirical equation for the volume of overtopping of seawall at the shoreline. And from this, next slide, these are the suggested design for rehabilitated breakwater in Hilo, Hawaii, on the left-hand side. Typical non-overtopping barrier section of a seawall at Hilo, Hawaii. These are constructed to prevent the tsunami waves coming inside. Next one. Yeah, you should not have the sloping protection. You see on the left-hand face of the first figure, left-hand face, it is practically vertical, but it has got a lot of indentations to absorb energy. It should not be sloping like the right-hand side, then the tsunami will come up and then height will develop, amplitude will increase. You see the stepped one on the right-hand side, the sea side, you see each one is practically vertical on the sea side. These are the tsunami resistant structures designed in Japan. Next one. Yeah, there's a cross-section of seawalls in 2 steps from Yamada, Japan. Next one. Now, when you are talking about design for tsunami, know your community's tsunami risk, hazard, vulnerability, and exposure. Avoid new development in tsunami run-up areas to minimize future tsunami losses. Locate and configure new development that occurs in tsunami run-up areas to minimize future tsunami losses. Design and construct new buildings to minimize tsunami damage. Protect existing development from tsunami losses through redevelopment, retrofit, and land reuse plans and projects. Take special precaution in locating and designing infrastructure and critical facilities to minimize tsunami damage. Plan for evaluation. All this, I said that there are a lot of similarities between the two, and great magnitude earthquakes lead to tsunami. And please remember, the Chile earthquake also had given birth to landslides. It also gave birth to a volcano 4 days after. Now, we are talking about the reservoir-induced earthquakes. If there is a sudden filling because of the climate change, in the case of Ediki Reservoir, I think the capacity is very high. There can be a small tremor, reservoir-induced tremor. So these are some of the things which we'll have to start investigating in the Kerala condition, though we are in the third zone now. Earlier we were not in the picture, but now slowly we are having some threats in Kerala also. So we'll have to take it into account. Friends, it has been a great pleasure for me to be in your midst to inaugurate this FDP. I hope that the proceedings of this, the classes and lectures given by the experts, will be of great use to each one of you. And at the end of the day, you should go out equipped with a lot of techniques and strategies to put an end to damages, safety to life due to earthquakes. Not only in India, not only in the Himalayan region, not only in the northeast of India, not only in China, but also in Chile, Japan, wherever you think your technology can help the humanity at large. Please strive for that. We are not doing it for Kerala alone. We are not doing anything for Tamil Nadu alone. We are doing everything for humanity. And I'm sure that some of the participants in this will come out with something innovative in the field of earthquake engineering and contribute to humanity and human welfare. I'm quoting Vintage Chow from the Open Channel Hydraulics book. his dedication to humanity and human welfare. Thank you very much.
Thank you, sir. Thank you so much, Dr. E.J. James, sir, for sharing such valuable insight to us. Your thought-provoking address with interesting examples and case studies and all set a perfect platform for all of us, sir. Thank you so much, James, sir, on behalf of Vidya Academy of Science and Technology, Thrissur, Kerala, and each and everyone present here in this online platform. Thank you. Thank you, sir.
Thank you, Abhilasha. Since I have to go to Coimbatore, I'll be leaving your session, but have a nice day, have useful discussions, deliberations.
Thank you. Yes, sir. Thank you. Thank you, sir. Thank you. Now, I invite Dr. Sudha Palagopalan, Dean Academics, Vidya Academy of Science and Technology, Thrissur, for the felicitation. Madam, please.
Thank you, Abhilasha. A very good morning to everyone here, especially our respected principal, Dr. Saji CB, the very distinguished person who spoke, the very distinguished Vice Chancellor of Karpagam University who spoke right now. In fact, the talk was not only illuminating, it was also thought-provoking. So that's a request that I placed before him. I hope Professor Abhilasha passes it on to him, such that we can access the slides and we can use our students to at least perhaps simulate a few of the situations that we talked about. Okay, moving on to all other. Thank you. Moving on to all our distinguished participants, including our own colleagues, as also colleagues from various institutions, as our vice principal, the very supportive trust members, which includes our directors, etc. I wish you a very good morning again. In fact, we noticed that though a kind of a climate was predicted, that is, we would have lightning as also heavy rains today and yesterday, it has not happened. But at the same time, we realize that things have not stabilized. Things are continuously at danger all over India. Okay, of course, Tamil Nadu might not have stabilized. Then again, Jharkhand always is an issue. The weather is always an issue there. And the people, and I noticed that, of course, my noting might not be fully accurate. What I noticed is that the going back to normalcy happens to be a little more difficult for humankind or mankind rather than for the other kinds of living things on our planet. Normalcy, it takes a long time to get normalcy established, especially because all the infrastructure that we have built happen to be affected whenever such issues come up. It could be plates moving, sometimes the road subsidence. It could be any kind of earthquake. Of course, earthquake is also okay. Of course, the recent concern is always the cloudburst and the landslides that are coming in. So infrastructure is always at stake. And in that sense, I'm very happy that quite a lot of discussions are going to happen in this venue about the importance of earthquake or in earthquake engineering, as was aptly explained by our distinguished chief guest a few minutes back. Moving on to what we can, okay, of course, moving on to this session, I hope that it is appropriately called as a faculty development program. And since I've been attending a few faculty development programs recently conducted by AICTE, I noticed that all technologies that are required for the build-up of the infrastructure, we definitely do need a lot of multi-engineering, a multidisciplinary kind of focus. I listened to trenchless technologies. I listened to the new techniques in waste management, to the power infrastructure, as also remote sensing in the last few days. And so I feel that even this session could have some kind of multidisciplinary kind of session, at least one session, especially because as an electrical engineer, I would say that earthquakes affect power structures in a different manner altogether. Of course, some precautions must have been taken. Like, for instance, even when we went to Assam, I noticed all those quaint buildings built on stilts because floods used to affect them every year. So similarly in Japan, the Tokyo Tower that we visited, I noticed, and in fact, I was listening to their explanation of all the precautions that they had put in the construct of the Tokyo Tower, especially because Japan happens to be earthquake prone. But at the same time, it has suffered. In 2011, it shrunk because the top portions were affected. So though we put in precautions, it continues to happen, as our chief guest right now spoke. Earthquakes will continue to happen, and so precautions will also be taken. Still, we may have problems, and that's the context in which such FDPs are situated, wherein we get updated. We also have to have discussions, not just sessions given by people, but also discussions, especially because discussions give rise to questions, searing questions, since infrastructure or any question in infrastructure affects not just the society, it affects the society, it affects economics, it affects the community, it affects the environment, it also affects, it is also, the impact is also politically based. So if we don't put together the scientific learning, the scientific understanding, put together and perhaps argue our way for a safer earth, then perhaps politics will have the say. So I hope, going back to the power structure, I hope we all realize that it is a little different. We have structures going down into the ground with the foundation, but at the same time, they are held together, or they are networked together via power lines. Okay, and there are kilometers and kilometers of power lines connecting them together, pulling this way, that way, etc., based on the wind. As also right now, if we think in terms of earthquakes, perhaps they are also affected. I really did hope that we had a session in this context also, but thankfully we are having a session in vibrations by none other than Professor K.B. Namboodiripad. So I'm eagerly waiting for that session, and I'm also hoping that the entire FDP is going to be a huge success with not just good sessions but also active listening, not passive listening, active listening, and questions will come, and those questions may not be answered, but the unanswered questions give room for more thoughts, more illuminating kinds of even more sessions to come later on. And I hope that the faculty development program will give rise to some teaching techniques that the teachers will take back to their institutions for giving more thoughts, or for giving more thought-provoking ideas to their students, because they are going to be the builders of tomorrow. They are going to be they are going to be our future. So with these few words, and wishing the entire faculty development program a huge success in terms of outcomes, in terms of interest, in terms of a better tomorrow. I thank the organizers for giving me an opportunity to talk, and I thank you all, and I rest my case. Thank you.
Thank you so much, Sudha Miss, for your suggestions, motivation, and blessings. Thank you, ma'am. Next, I would like to invite Dr. V.N. Krishnachandran, Vice Principal and Head of MCA Department of WAST Thrissur, to address the gathering. Welcome, sir.
Okay, good morning, all of you. Respected dignitaries who are attending this inaugural session of the Adali FDP organized by the CE Department, Civil Engineering Department of India Academy of Science and Technology, and the participants from different parts of India. I am happy to be a part of this inaugural ceremony. I watched with much interest the great talk by Engineer James Sir, which he delivered as an introduction to earthquake engineering. The concluding words were so inspiring to me also. He was talking about all the work that we do being for the welfare of the humanity as a whole. What we do is not for Kerala or Tamil Nadu or to India, but it should be dedicated to humanity. So that is a message. Perhaps I may be aware of such a message, but he articulated so profoundly that I hope and we shall be carrying that wherever I go. Okay. Now, regarding FDPs, see, Vidya, the faculty members of Vidya are associated with the AICTE sponsored FDPs in several ways. Faculty members have been organizing faculty development programs. They have been serving as resource persons in FDPs held in other institutions. And a large number of faculty members have already attended FDPs like this. And that is an indication of the vibrancy of the academic life in the campus. I hope this FDP will give an impetus to sustained learning on this topic. And this will give an occasion to start more dedicated work in areas related to work. I am looking forward to a time when this institution becomes a center of research in earthquake engineering. That is one of my dreams. So I hope the FDP that's being currently organized will provide the platform, will provide the basis for such a venture. I congratulate the MCE department. Especially, I congratulate Dr. Abhilasha PS for taking all the trouble, for taking the concept to the ACT, getting things sanctioned, and organizing it in such a nice way. And also getting together a galaxy of experts to address the participants. So it will be very enjoyable. It should be very enjoyable and should be a very good learning experience. So I conclude all success, and by saying, wishing all success to the program, and also wishing you happy learning. Thank you.
Thank you, dear sir, for your encouraging words and blessings. Thank you. We are now in the end of the inaugural session, and as a coordinator, it is my duty to thank all those who have helped us to make this auspicious beginning. We are really honored to have this wonderful inauguration today. First, our humble thanks to Chief Guest, Dr. E.J. James, who honored this function with his gracious presence and inspiring thoughts. Sir, there are many fans of you in this gathering, and you are very much inspired by us. We are inspired with you, that is by you. And I thank you very much in your absence also on behalf of Vidya Academy of Science and Technology, Thrissur, and from all participants present in this online meeting. Next, I would like to thank distinguished speakers attending today's inaugural function. Thank you, sirs and madams. We are anxiously waiting for your sessions and to learn from you all. Now, I would like to thank our Executive Director, Mr. Suresh Lal sir, Administrative Director, Mr. Unirajan sir, Honorary Advisor Mohan Chandran sir, Chairman Santosh Prasannan sir, Chief Patron Ashokan sir, and all members of Vidya International Charitable Trust for all support given to us. Our principal, Dr. Saji CB, is always with us, giving support and guidance. On behalf of FDP coordinating team, I would like to thank you, sir. Now, I would like to thank our Dr. Sudha Balagopalan, Dean Academics, and Dr. V.N. Krishnachandran, Vice Principal and Head of the LCA Department, for the felicitations given. Thank you, Madam and Sir. Next, I would like to thank heads of all departments, teaching and non-teaching staff and students for attending this inaugural function. Now, I would like to thank technical support team led by Mr. Shai. We need your support throughout the FDP till the end of validity function also. Next, I would like to thank all the 85 participants from various parts of the nation who joined in this online platform for selecting our FDP, Recent Advances in Earthquake Engineering. Without you all, it is not possible to have this FDP now. So thank you all from the bottom of my heart. I shall quickly share few important points about program. This is 5 days FDP, and each day we'll be having 3 sessions of 2 hours each, and a validity function at the end of 5th day. Attendance should be marked digitally, so please attend all the sessions. And online tests will be there at the end of every session, and feedback on test links would be given at the end of each session. Link will be open till 11 p.m. each day. So also you have to please switch off your camera and audio during the sessions. You can ask questions at the end of every session. 30 minutes is there for discussions. Okay, then you are requested to log in with your registered email ID also. Okay, then for any queries, you can contact the WhatsApp group created, and also you can contact the numbers given in the brochure. All the session PPTs, learning materials, videos, etc. would be shared with you, all of you, at the end of the FDP. And participant certificates will be issued by AICT Atal for those who successfully participate with 80% attendance and 60% score in the test. And also after filling the feedback form in the AICT Atal portal. Also, we will definitely like to hear from you all during the end of the sessions, that is during the validity function on the 5th day. Now, coming back to my responsibility, I would like to thank our head of the department, Civil Engineering Department, and coordinator, Dr. C. Justin Jose, and entire team of civil staff, especially Nisha Varghese, Adra P. Nair, Ampili, and Kiran, who helped to make this program a beautiful one. I would also like to thank AICT Atal officials who accepted our proposal and helped us to arrange this FDP on recent advances in earthquake engineering. Once again, I thank each and every one of you present over here in this online platform from the bottom of my heart. Enjoy the coming sessions and get benefited yourself. Stay safe and take care too. Thank you. Namaste. Thank you all. We'll start our next session in 5 minutes. So please wait for 5 minutes. Thank you all.
Is my screen visible? Hello?
Yes, sir. Good morning, sir.
Good morning.
Yes.
Good morning.
Yeah, screen is visible, sir. We'll start by 10:45.
Yeah,
It's
let me see
10:42 now.
whether PPT mode I will convert.
Is visible, sir?
Visible. Okay.
Yes. Perfect now. Okay, shall we start now, sir? Hello? Cutter, sir?
Hello. Yes, madam.
Yes. Shall we start now, sir?
Yes, please.
Okay. So welcome back to the FDP on recent advances in earthquake engineering. With us, now we have our resource person, Professor Katta Venkatramana, a senior professor at Department of Civil Engineering at NITK Surattal. And his topic is Engineering Seismology and Learning from Past Earthquakes. So, Professor Katta Venkatramana is a senior professor at the Department of Civil Engineering, NITK Surattal, as I told earlier. He did his bachelor's degree from University of Mysore and master's degree from Kagoshima University, Japan, and doctoral degree from Kyoto University, Japan. He did his postdoctoral research fellow at the University of Oxford, UK. He worked as head of the Department of Civil Engineering at NITK 2 times during 2009, 2010, and from 2013 to 2014. He worked as Dean Academics and Chairman for Board of Studies at NITK during 2014-2017. And his current research interests include structural engineering, particular structural dynamics, and earthquake engineering. 19 scholars have completed a PhD degree under his guidance, and he's a fellow of Institution of Engineers India, and he served as the chairman of Institution of Engineers India, Mangalore Local Center during 2018-2021, and Eminent Engineers Award. He received Eminent Engineers Award from the Association of Consulting Civil Engineers in 2013, and Scholar of Honor from the Institution of Engineers India in 2021. Now, I welcome you, sir, to this program, our first session coming under this FDP. Welcome, sir. Please. Now your stage is for you, sir. Please come.
Thank you, madam, for the nice introduction. It's an honor for me to be part of this FDP. Can you see my screen? Hello?
Yes, sir. Please put in slideshow mode. Yes, sir. Yeah, it is perfect now. Yes, sir.
Yes.
Please continue.
I'm very happy to be part of this FDP program, and also we had a very interesting opening remarks. The inaugural speech, inaugural address by James sir, our own NITK alumni. He explained about the earthquake engineering in a nutshell, and also his specialization regarding tsunami he explained. My lecture also, it is mostly introduction, engineering seismology, and also we'll study, we'll see some of the experiences from the past earthquakes. Just for the sake of completion, the definition, vibration of the Earth's surface caused by waves originating from a source of disturbance in the Earth mass is called earthquake. Earthquake may be caused by a volcanic eruption or by a strain building process inside the Earth mass. The main thing is earthquakes are unpredictable. Earthquakes are unpredictable, although the possibility of earthquakes where we have the experience, previous experience of occurrence of earthquakes, the possibility is more. And man-made earthquakes, main industrial activities which can also induce or trigger seismicity earthquakes, like hydrocarbon storage and extraction, shale gas exploitation, geothermal energy exploitation, then mining operations, carbon dioxide sequestration, the storing of carbon dioxide from the atmosphere in deep within the earth, and also dams. Dams, as Professor James also mentioned, can induce pressures in fissures, and they can trigger earthquakes. And tsunami happens when the source of the earthquake is underwater, and the wave height increases as tsunami waves approach the coastal region, And in such a case, there can be a lot of damage, as Professor James mentioned in the case of Chile earthquake in 1900s. We'll quickly go through how the earthquakes occur. If you look at the Earth's structure, we have Earth's crust, then mantle, then core, outer core, and then inner core. So this outer core is mainly liquid and mantle in the plastic stage. And with regard to the temperature, if you come to this right hand diagram, inner core around 4,300 degrees centigrade, and then outer core 3,700 degrees centigrade, mantle 1,000 degrees centigrade here, and then we have the Earth's crust, atmospheric temperature. So there is lot of temperature variation and also pressure variation, and this results in convection currents, as you can see in this figure. It is like when you warm water in a beaker, you see it gets heated up, goes here, cools down, comes back. So like this, movement takes place, as you can see here in the animation. Can you see the animation here? Hello?
Sir? Yes, sir.
Animation, are you able to?
Yes, sir. Yeah. Yeah. We can see.
Okay. So in this way, convection currents take place because of the temperature gradient and pressure gradient. And the Earth's surface is consists of several plates which move in different directions, and most of the earthquakes occur along the plate boundaries. And here we'll discuss the definition of magnitude later. Only some numbers is you can see here. The bigger the number, it indicates the larger is the magnitude of earthquakes. So as outermost surface is broken into several rigid plates which float on top of a more fluid zone, much in the way that icebergs float in the ocean. About 225 million years ago, the continents were joined into one supercontinent that Wegener, the seismologist Wegener called Pangea. And with the passage of time, this divided into two large subcontinents, Gondwana land and Laurasia. And in the great subcontinent Gondwana land, South America and Africa were connected with each other, and with Antarctica, India, and Australia. This is roughly the time when the first flowering plants began to appear on Earth. You can see South America, Africa are connected, as well as with Antarctica, India, and Australia. By 65 million years ago, about the time when dinosaurs became extinct, continents had divided into positions closer to the present-day configuration. So this shows the animation, how the one supercontinent divided into several continents with the passage of time in millions of years. And when, okay, this shows the present tectonic plates. There are 7 major plates. So North America, South America, Eurasia, Africa, Pacific plate, Australian plate, and Antarctic plate. They move a few centimeters a year, riding on semi-molten layers of rock underneath the crust. And most of the earthquakes have occurred along these plate boundaries, which we call intraplate earthquakes. So the movement of plates is shown here. Sometimes they move apart. Sometimes they move side by side, as you can see here, Pacific plate and North American plate, side by side. And sometimes they collide, like Indian plate colliding with the Eurasian plate. So resulting in mountain formation. And when they move away from each other, there will be formation of valleys. As the plates move, they pull apart or collide, unleashing earthquakes along their boundaries. And you can see valleys forming, mountain building, sea floor spreading, and so on. This is San Andreas Fault Zone in California, 1,000 kilometers long fault system. This marks the boundary of North American and Pacific plates. Also, we have a lot of volcanoes around the, mainly around the Pacific plate, and we call this ring of fire. Even in today's newspaper, there was mention about volcano in Indonesia. Indonesia, and several people lost their lives because of the sudden eruption of the volcano. So volcano in New Zealand, Indonesia, Philippines, Taiwan, Japan, then Alaska, western part of America, Central America, Peru, and then Chile. You can see is this is Japan actually. Eurasian plate, Pacific plate, and Philippine plates collision. All these red line indicates the occurrence of earthquakes, presence of volcanoes. So one of the volcano here in southern part of Japan is shown here, the eruption. It's called Kagoshima City, where I did my master's and I worked also here for quite many years. So when there is no eruption, the mountain looks like this, only a base separating, and we have these kind of eruptions from time to time. And then this is one of the photographs taken at night, the lava flowing out. You can see the eruptions clearly. Now coming to the earthquake measurement, there are mainly two terminologies, magnitude and intensity. Magnitude estimates the amount of energy released at the source of the earthquake. Commonly used Richter magnitude scale. This is the scientist Charles Francis Richter who proposed this scale. Quantitative measure of earthquake. Whereas intensity, it is a measure of the degree of earthquake shaking at a given location based on the amount of damage. By observing the amount of damage, we give a value. Commonly used Mercalli intensity scale or modified Mercalli intensity scale. It varies from 1 to 12. 12 is the maximum damage intensity, whereas Richter magnitude estimates the amount of energy release. It is quantitative and it's an open-end scale. Anyway, so far observed is the maximum is Chile earthquake, 9.5 magnitude. So same thing is explained here. Quantitative measure of the actual size of the earthquake. An increase in magnitude by 1 implies 10 times higher waveform and 31 times higher energy release. So for instance, energy released in 7.7 earthquake is about 31 times that released in 6.7 earthquake, or 1,000 times energy released in magnitude 5.7 earthquake. So when the number changes like M5.7 to M7.7, it is about 1,000 times more energy being released. Taken from the earthquake tapes. National Information Center for Earthquake Engineering. We can get a lot of information about earthquake engineering from this website. And the frequency of occurrence of earthquakes, this red is actually damaging earthquakes. Magnitude 6 to 6.9, about 134 earthquakes in a year, somewhere in the world. 7 to 7.9 magnitude, around 17, and at least one earthquake of magnitude 8 and higher. Whereas there are a lot of minor earthquakes, like very minor, magnitude 2 to 2.9, around 13 lakh earthquakes. These are mainly measured by the instruments and give an indication of the seismicity of the region. We are mainly bothered, as civil engineers, we are mainly bothered from moderate to severe earthquakes, which can cause extensive damage to life and property. Some of the greatest recorded global earthquakes, Chile earthquake happened in 1960, magnitude 9.5. And Alaska earthquake, 1964, magnitude 9.2. Then Indonesia earthquake, some of you may remember, 2004, which caused extensive tsunami. More than 2 lakh people died, and even in Indian coasts, in Tamil Nadu, Kerala, all people experienced damage due to this tsunami, and Sri Lanka also. And then Japan earthquake, 2011, a lot of people died, not only due to earthquake, but also tsunami-induced damage. Indonesia, again 2005, magnitude 8.6. China, magnitude 7.9 in 2008. And in Central America, Haiti, one of the poorest country in Western Hemisphere, 2 to 3 lakh people died, it seems. Magnitude only is 7.1. So this shows the global epicenter map of earthquakes from 1900 to 2017. Shows the occurrence of severe earthquakes, magnitude 6 and higher. So this is the Chile earthquake here, Alaska earthquake, Indonesian earthquake, then Tohoku, Japan earthquake. Now, with regard to intensity, although each earthquake has a unique magnitude, that's one number giving the energy release, intensity, its effects will vary greatly according to distance, ground conditions, construction standards, and other factors. The earthquake intensity or earthquake effect will vary as we go away from the source or epicenter of the earthquake. So intensity should not be confused with magnitude. Intensity is an arbitrary ranking, and it gives the actual shaking during an earthquake. This is from the Bhuj earthquake. This map joining points of equal intensity we call isoseismal map, and these are isoseismal lines. So intensity 10, intensity 9, intensity 8, intensity 7, and so on. So this is actually taken from an educational brochure from Nepal, intensity varying from 1 to 12. 1 is not felt except by very few under especially favorable conditions. Intensity 2 felt by few persons at rest. Only who are quiet will feel it. Intensity 3 felt quite noticeably by persons indoors, especially in the upper floors of buildings, because upper floors will shake more. And intensity 4 felt indoors by many, outdoors by few. And intensity 5, shaking is felt by nearly everyone. Intensity 6 felt by all, many frightened, some heavy furniture moved. Intensity 7 and 8. Intensity 7, damage negligible in buildings of good design. Intensity is 8 means damage slight in specially designed structures, but considerable damage in ordinary buildings. Even partial collapse may be there, and damage great in poorly built structures. And intensity 9, damage considerable in specially designed structures, and damage great in substantial structures with partial collapse, buildings shifted off foundation. And intensity 10, some well-built wooden structures destroyed, most masonry and frame structures destroyed with foundations rail bent. In Bhuj earthquake, we saw this intensity 10 near to the epicenter. Intensity intensity 11 and 12, damage is very high. Few, if any, structures remain standing, we just destroyed. And the damage is total. Lines of sight and level are distorted. Objects thrown into air. This is intensity 12. So these are the intensity. An attempt is made here to compare the magnitude and intensity. it is near to the, when the intensity is close to the epicenter, we can take this correlation. So intensity 1, 2 means generally not felt, but recorded on seismometers, that's instruments, about 2.5 magnitude. Similarly, intensity 6, a destructive earthquake, and the magnitude is 6, destructive earthquake, intensity vary from 8 to 9. And a great earthquake, magnitude 8 and out, intensity corresponding to 11, 12 near the epicenter. Almost all structures fall. So earthquakes measurement, there are two scales, Richter scale and Richter magnitude scale or magnitude scale and intensity scale. Commonly used magnitude scale is Richter scale, and commonly used intensity scale, Mercalli scale, varying from 1 to 12. Whereas magnitude scale is open-ended scale, and above 6 will be severe earthquakes. Now let us come to our Indian plate movement. In the beginning, I showed you the plate tectonics movement of the plate. So Indian plate was away from the Asian plate. This is like 71 million years ago. So it has moved northwards, as you can see here. This is the present day configuration. Geographical layout and tectonic plate boundaries. So this is the boundary of Indian plate. So most of the earthquakes in India have occurred along these plates, which we call interplate earthquakes. Now, birth of the Himalayas is explained here. About 60 million years ago, India collides into the Asian plate. This movement is what eventually causes the Himalayan range, as the two plates push against each other and the Earth's crust is squeezed upwards. You can see there was sea here, Tethys Sea, and this is the Indian plate. This is the Asian plate. They are colliding with each other. So sediments push upwards. This is 60 million years ago. Say, this is 40 million years ago. Sea has shrunk and sediments have moved upwards. And Indian plate is colliding, moving deeper into Tibet. So mountains start forming here. You see 60 million years ago, 40. Sorry. So this is 60 million years ago, 40 and 20 million years ago. Already the sea has vanished here. Tethys Sea is completely gone. Heavy sediments from the ocean floor are pushed upwards and Tibet begins to rise. And this is today. Through GPS technology, we know that 19 kilometers below the surface of the Earth, India continues to move northward under Tibet at 18 mm per year. The greater Himalayas, including Everest, are rising approximately 5 mm per year as a result of this squeezing motion between India and Tibet. And seismologists predict that 10 million years from now, as the boundaries of Nepal approach each other, Nepal ceases to exist. The Himalaya, however, still exists as foothills and mountains continue to form over the advancing edge of India. In this way, Indian plate is moving continuously under the Tibetan plate, and the Himalayas are rising. This slide shows the seismicity of India. All these red circles indicate the occurrence of earthquakes. So mainly along this northern plate boundary. But again, we have earthquakes away from northern plate boundaries also. These are called intraplate earthquakes within the plates. So this is Kerala region here, Tamil Nadu, Karnataka, and here near the Koina Dam, Koina area also, lot of earthquakes. This is mainly a reservoir triggered seismicity. And this shows the right-hand side map shows the tectonic map of India. All these lines show actually the fault zone, fault line. And many earthquakes have occurred along this fault region. Some of the largest Indian earthquakes, earlier we discussed the global earthquakes. In India, 1819, in Kutch region, magnitude 8 earthquake, maximum intensity 9 had occurred. And 1833 Bihar earthquake, magnitude 7.7, intensity 10. 1897 Assam Shillong earthquake, magnitude 8.7. Then again Himachal Pradesh, magnitude 8, magnitude 7. Then 1930, Meghalaya, magnitude 7.1, heavy damage occurred. In 1934, Bihar, Nepal, magnitude 8.3. 1941, Andaman Island, magnitude 8.1. These are some of the largest Indian earthquakes. Of recent 1943, Assam, magnitude 7.2. Then Arunachal Pradesh, China border, 1950, magnitude 8.5. And then 2004, December 26, we had this Indonesian earthquake, magnitude 9.1. And also 7.7 Gujarat earthquake, 2001. 2011 Sikkim Nepal border, magnitude 6.9, and Nepal earthquake 2015. I have some photographs of damage from some of these earthquakes which I show later. This map shows the seismic zoning map of India as per IS 1893 code, earthquake risk and design code, latest revision in 2016. Our country is divided into 4 seismic zones, zone 2, 3, 4 and 5. And if you look here, zone 3, moderate risk zone, magnitude 6.9. And then, so here this yellow comes in magnitude, we can expect earthquakes up to magnitude 6.9, zone 3. So Kerala, parts of Karnataka, parts of Tamil Nadu, Andhra Pradesh here in the southern part of India. And then Mumbai region, parts of UP, Bihar, West Bengal, they come under zone 3. Then zone 4, high risk zone, magnitude up to 7.9 we can expect. This area here. Then Koina area, parts of Kashmir, UP, Uttaranchal, Bihar. We can, Delhi comes in zone 4. You can see here, zone 4. Then zone 5, very high risk zone. We can expect magnitude 8 and greater. Entire northeast comes in zone 5. Parts of Kashmir, Uttaranchal, then parts of Gujarat. Kutch region comes in zone 5. So around about 65% of our country, more than 65%, more than 60%, sorry, of our country comes in in moderate to very high risk zone. Moderate to very high risk zone, and it is very much important that we consider earthquake resistant design in our all construction aspects. So this is just to give an idea, pseudostatic analysis I have shown here. If W is the vertical load, for the horizontal load, earthquake induced load, for example, we can consider this for an approximate value, W into Z, where Z is the zone factor. So zone 2, 0.1, that means if there is 100 kilonewton W, the horizontal zone, horizontal load, or the load due to horizontal excitation, we can take 10%, 0.1 or 10 kilonewton, where the same, for same W, if you are constructing in zone 5, we may have to consider 36 kilonewton as the horizontal load. In this way, depending on the zone, depending on the seismic zone, the value will vary. And of course, the soil characteristics, importance of the structure and type of the building and so on, the value of H will vary. The guidelines are given in IS 1893. I'm just explaining here as a approximate calculation value. Now, some more aspects of seismology. As I mentioned, faults, many earthquakes have occurred near faults in India also. Faults are narrow zones in the earth. Earthquakes can also occur far from edges of plates, but along these faults, far from edges of plate boundary. That's what I'm telling here. So they can occur along faults. Faults are cracks in the earth where section of a plate or two plates are moving in different directions. And faults are caused by all that bumping and sliding that plates do. And they are more common near edges of the plates. So this is a fault line. And this is the focus or point where the earthquakes start or fault rupture starts. Point vertically above on the ground we call epicenter. And the fault motion, there are 4 types here. So this is the fault line. And deep slip fault or normal fault, the block above the fault moves down relative to the block below the fault. Especially if in underwater earthquakes, as Professor James mentioned, if this kind of fault movement occurs, the probability of occurrence of tsunami are more. This fault motion is caused by tensional forces and results in extension. And reverse fault, in a reverse fault, the block above the fault moves up and relative to the block below the fault. This fault motion is caused by compressional forces and results in shortening. So these deep slip faults, both normal fault and reverse fault, result in tsunamis in the case of underwater earthquakes. Then strike slip fault, here the movement of blocks along a fault is horizontal and it is caused by shearing forces. So if this is the road here, you can see how it changes. And here oblique slip fault, it is combination of shearing, tension and compressional forces. This is some examples of fault motions. Then some terminology. Focus, the point on the fault where slip starts. Focus, or in some literature it is also mentioned as hypocenter, and point vertically above, we call this epicenter, and the depth is known as focal depth. The depth of focus from the epicenter is an important parameter in determining the damage potential of an earthquake. Most of the damaging earthquakes have shallow focus with focal depths less than 70 kilometers, about 70 kilometers or less. So you can expect large shaking and large damage on the ground. And distance from the epicenter to the point of interest, we call this epicentral distance. And effect of earthquakes is when there is a energy release at the source, it will create earthquake waves or seismic waves. Seismic waves which travel within the earth we call body waves or deep waves, and waves that travel along the surface we call surface waves. So when these body waves reach the surface, they travel along the surface. And these body waves, there are 2 types, primary wave and secondary or shear wave. And then along surface also we have 2 kinds of waves, love waves and Rayleigh waves. So here the particle motion is different. This is shown in the next slide. Body waves. We have, this is undisturbed material, and when the primary wave progresses, there is alternately compression and expansion along the wave propagation direction. Whereas for the secondary wave or shear wave, there is particle motion at right angles. That is mentioned here. primary waves. Fastest waves travel through solids, liquids, or gases. And compressional wave, material movement is in the same direction as wave movement. Whereas in the case of S waves, they are slower than P waves. They travel through solids only. And shear waves move material perpendicular to the wave movement. Then we have the surface waves, which travel along the surface. Then the particle motion is sideways in horizontal plane. We call this, you can see here also. And when they move in elliptic form, we call this Rayleigh waves. Particle motion is in elliptic. Travel just below or along the ground surface, the surface waves, slower than body waves, rolling and side to side movement, and they are especially damaging to earthquake structures. So you can see the animation here, the particle motion, primary waves. This is S waves at right angles. Then this is love waves. Particle motion is sideways, and Rayleigh waves, it is elliptical motion. So this animation shows how the particle motion are different in these 4 types of waves. And mostly the surface waves and secondary waves, shear waves, where the particle motion is at right angles to wave propagation, they will cause a lot of damage. Same thing is shown here, how it affects the building. Also, these waves get transformed, amplified when they pass through soft soil. Wave may travel thousands of or hundreds of kilometers along rock without amplification, but only few kilometers within the soil, waves are amplified. You can see in this right hand also, amplified, and shaking will be more, and there will be more damage to the buildings. This is seismograph. The instruments that measure earthquakes, we call seismographs. Due to time, I will go a little bit quickly. Here, this is horizontal seismograph. You can see as the waves, seismic waves arrive. Okay, primary wave arriving, followed by waves. Similarly, this is vertical seismograph. So recording device is vertical here. And as the waves move, as the waves arrive, they are recorded on the instrument. These are the schematic diagram. But now we have very sophisticated instruments, seismographs. Today, seismometers operate by measuring the amount of electrical energy needed to keep the mass centered in the housing in the presence of strong ground shaking, and they can record a wide range of seismic signals, both very small and very large. So they actually measure the electrical energy required to keep this mass in the center position. The principles of modern seismometers. And the record of seismograph, we call seismogram. A seismogram is a record of the ground shaking recorded by a seismograph. At a location, P waves travel fastest. So they arrive at a seismograph first. So initially we have primary waves, followed by the secondary waves, and then we have the surface waves. And most of the shaking is observed when the surface waves arrive, and it is random in nature, time dependent, and cyclic motion will be occurring. This is actual record during the Bhuj earthquake, 2001 Bhuj earthquake, recorded in a building called Passport Building in Ahmedabad. You can see this acceleration record, and here we have displacement from about 30 seconds to 60 seconds. This is actually strong motion, and most of the damage occurred due to this, around 30 seconds of earthquake. And locating the shaking, seismologists locate earthquakes by measuring the time between the primary and secondary waves in a seismogram. After a seismogram feels an earthquake, scientists compare the time difference of these waves to figure out how far away the earthquake is. For example, this seismograph, noting the time difference between primary wave and secondary wave, we say earthquake has occurred around 4,800 kilometers. So we draw a circle. And this seismograph says 2,800. So draw a circle. We have two meeting points. So source may be, earthquake source may be here or here. And if we have one more instrument, measuring the time difference between primary and secondary waves, say 3,400 kilometers. So if you draw a circle here, so this will indicate the source of earthquake, exactly where the earthquake has, the source of the earthquake is located. So by measuring the SP times at 3 or more stations, these circles can be drawn around each station, and where they meet indicates the earthquake location. So this travel time in minutes, here distance to epicenter. So primary wave at the location here occurred here, and secondary wave say after 5 minutes. So based on this, we can estimate the distance. So for example, here they are indicating epicenter of the earthquake. We have the instrument here, say here Paris, here, and at this location Sao Paulo. So we can draw circles noting the time between P wave and S wave, and we can locate the epicenter. Now that is about the engineering seismology. I have covered mainly about the seismology aspects for which are required for us. Now I will show some of the earthquake damage photographs. Madam, how much time I have? Up to 12 o'clock?
Yes, sir. Yeah. You can continue till 12, sir.
Okay, okay. I will skip some of the slides. This is from the earthquake damage during Bhuj earthquake. Typical failure patterns identified in a masonry building. Separation of roof from wall during Bhuj earthquake. Also failure of junction of two orthogonal walls in unreinforced masonry building. This is from 2011 Sikkim earthquake, magnitude 6.9. In earthquake resistant design, we provide so-called bands, which are wooden beams or RCC beams at regular intervals at plinth level, lintel level, roof level. They will help the building to behave as a single unit. In the case of pitched roof, we will provide proper connections apart from this lintel band and plinth band. So the building which is having this lintel band, plinth band, they have performed well during the earthquakes. This is from the Bhuj earthquake. There may be cracks developed which can be easily repaired, non-structural cracks. So those buildings have withstood, but without horizontal bands, buildings have collapsed. This is from 1993 Latur earthquake. One masonry house in Kilari village had a horizontal lintel band and sustained the shaking without damage. Whereas here, without horizontal lintel band, we can see the collapse of the roofs and damage to walls. So these bands will help for the building to behave as a single unit. And we will have box action. Some of the other damages here, partial collapse of stone masonry wall during 1991 Uttarakhand earthquake. This is out of plane failure of walls in 2015 Nepal earthquake. And this is from the Bhuj earthquake, the wall flexure. The following typical types of damage can be identified in a masonry building. Say this is the direction of seismic action. So cracks between walls and floors, cracks at corners and at wall intersections, out of plane collapse of perimeter walls, diagonal cracks in structural walls, these kinds of diagonal walls, then this kind of collapse, out of plane collapse, direction which is perpendicular to the direction of seismic action. We call this out of plane motion, out of plane bending. So the walls along the, which are along the earthquake direction, here we can see these kinds of shear cracks, diagonal cracks being developed in the walls. Then partial disintegration or collapse of walls, or partial or complete collapse of building. In Bhuj earthquake, in Ahmedabad itself, 132 low to medium rise structures collapsed. RC walls with unreinforced masonry, they are most common in our country. This can be anywhere in any major cities in India. And some of the failure pattern, one is soft story effect, open ground story. For parking, normally we provide open space here. If these columns are not properly designed, we can expect the crushing of this ground story as happened here. In soft story collapse of the right wing of the building, the left wing without soft story is apparently undamaged here. So if we design, if we don't consider masonry infills, this may be the expected deformation. However, because of this open ground story, these columns are subjected to large deformations here, severe deformations. This will result in collapse of these columns. So this right hand side, this is Sayaji Hotel, Gandhidham, it failed at the ground story. And then short column effect, when we have walls built up to certain height, these become short columns. If we don't provide sufficient stirrups, they will be fail like this. They attract large shear forces. And here cracks developing in the walls. So walls have failed here. This is Manipur earthquake. So predominantly when there are no masonry infills, it will be predominantly frame action, whereas this masonry infills, this will result in predominantly shear action, and we can, when it is subjected to motion in alternate left to right and right to left, then there will be this compression and tension alternately along the diagonals, and then cracks will develop and wall may fail. Another is due to honeycombing. You can see when we do concreting, we will do up to, for columns up to certain height, and top portion of the columns and beams above, they will be, concreting will be done together. But due to reinforcement, flow of concrete is difficult, and there can be honeycomb formation. And when the construction is complete and all the plastering is done, we will not know what is the inside condition. But when subjected to earthquakes or natural disasters like this, we can see the failure happening. And this is also same. Lack of lateral ties, you can see no stirrups at all provided. And here also the distance is too much. More than the minimum amount specified in the codes. Then anchorage, if you look at the codes, the anchoring of reinforcement bars, this is like development length plus 10 times the diameter of bars, this has to be done. But if you look actual construction, very haphazard way or very small anchorage length we can see, and many buildings fail because of this problem. Then short column effect, this is a factory near Kandla port. all peripheral columns, we can see the damage like this, whereas inside columns, they performed well. This I will skip. Then I will explain some of the earthquakes from abroad. The Chile earthquake, which Professor James was also mentioning, 1960 Valdivia earthquake. This Valdivia city founded as early as 1552 by Spanish explorers. Also, it's also called a city of the lake. And the 1960 Chilean earthquake, magnitude 9.5, which is the largest event in modern history. And 3 distinct hazards were observed. Strong ground shaking, tectonic subsidence, and tsunami was also caused. And tsunami indentation occurred because of this. Casualty around 6,000 people. So this is the Chile here. Tsunami, this shows the time in hours. So after 2 hours, 4, 6, 8, etc., hours after start of the tsunami, it reached Hawaii 16 hours after the occurrence of earthquakes. And then Japan here, Japan, Philippines, all around 22 hours after the occurrence of earthquakes. Nowadays, anyway, there is a good communication network, so people can expect when the tsunami can occur, and the tsunami can be simulated also. People can get an idea what would be the indentation region, and people can be evacuated. But during those times, it was not there. A lot of people lost lives. And this photograph shows how the liquefaction occurred. Liquefaction occurred, cracks develop on the roads network. And you can see the depth of crack here, and damage occurred. Here, the city is underlain by interlayer sands and silts having moderate to high plasticity. The surface topography of the city has been modified over time, and low spots filled by low and high plastic silts experienced ground failure. That is about the Alaska. This is about the Alaska earthquake, 1964, magnitude 9.2. Lateral spreading here caused the distortion of the railroad tracks. Also here, a steel truss railway bridge across the river Rio Bananito, located in the foothills about 20 kilometers inland. The lateral spreading of the banks destroyed the caisson foundations supporting the structure, allowing it to drop to the banks. Then Niigata earthquake, 1964, magnitude only 7.3, but caused extensive damage due to liquefaction. Some of the 4-story buildings in the Kawangi Shichijo apartment complex settled and tipped as much as 60 degrees, you can see. A loss of bearing strength was caused by liquefaction of a sand layer 10 to 15 feet below the base of the affected buildings. The peak ground acceleration did not exceed 0.1 g in the earthquake. However, due to this liquefaction, damage has occurred. And after this 1964 earthquake, people realized the importance of geotechnical earthquake engineering, and a lot of research has started. This is 1971 San Fernando, California earthquake. Here also freeway underpasses have failed at certain locations. Maybe soil conditions have resulted in these failures. Aerial view of a collapsed section of the dam here, lower one Norman Dam at this location. Also here failure of San Diego freeway overpass. This earthquake reinforced the need for bridge designers to consider strong ground shaking as well as the ground failure effects. Then Mexico earthquake, 1985. Mexico earthquake struck at early morning on 19 September of 1985. Earthquake occurred with a magnitude of 8.1 and maximum intensity of 9. And the city suffered major damage due to large magnitude of the earthquake and ancient lake bed that Mexico City sits in. This is the epicenter of earthquake, quite far from Mexico City. However, a lot of damage occurred in the Mexico City. Mexico City area. Okay, Mexico City area was 350 kilometers away from the epicenter, but still it caused widespread damage in the city. If you look at the distance, you say this is at the beginning, the seismogram. If this will be a plot away for around 13 kilometers, 27 kilometers, 50 kilometers, like this, supposed to die down as we move away from the hypocenter or focus or epicenter of the earthquake. However, in the case of Mexico, it didn't happen. If a seismic wave were traveling through uniform material, ground shaking would be half as strong at 13 kilometers, 1/4 strong at 27 kilometers, and 1/8 as strong as 50 kilometers. However, in the case of Mexico City, it's a sediment-filled basin surrounded by hard volcanic bedrock mountains, this area. As waves progress and move towards the softer bed, basin amplification occurs, that is having low frequency and high amplitude. So this is the ground motion, high frequency, low amplitude away from Mexico City, whereas when it approached here, we have low frequency and high amplitude. So this has shaken the soft sediments of the ground like a jelly in a ball. The natural period of different buildings is shown, which represents difference in resonance period, like small building, high-rise building, medium-rise building. So the natural period is different. In Mexico City, earthquake, as the ground was oscillating at 2 seconds time period, ground period was 2 seconds, the building of 8 to 20 stories with similar natural period suffered the most damage. So the earthquake shaking was around 2 seconds per 2 seconds time period, and the natural period of buildings 8 to 20 stories is in that range. So these buildings suffered maximum damage. Some of the photographs of this damage of the buildings. In some cases, damage was caused by adjacent building banging against the wall and supporting the column, which we call founding effect. So most of the earthquake damage to the buildings, the two reasons are the resonance in the lakebed sediments and the long duration of the shaking. Mexico City had one of the most stringent building codes based on experience from the earlier earthquakes from 1957 to 1979. Still, a lot of damage occurred here because of these soil conditions. Some foundations experienced damage, such as pile driven into clay, which was held in place by friction, turned out to be weak. The design resistance was not enough because pile was not driven up to hard ground, but mainly depended on the friction effect. Okay, some more photograph. This is 1988 Armenia earthquake, Europe. Damage to unreinforced masonry building. Magnitude was about 6.8. Then 1992 Turkey earthquake. Severely damaged, nearly collapsed residential building. Many failure forms such as column shear, joint shear, lack of bar anchorage, all were observed in this case. Then 1995 Kobe earthquake in central Japan. The Kobe earthquake occurred early morning. People were preparing breakfast and a lot of wooden buildings in Japan. So they experienced extensive damage because of the fires, post-earthquake fires. So some damage to the highway here. Aerial view of the Hanshin Expressway with two spans fallen off supporting piers. Several of these collapses occurred at the locations right next to a canal. This is a canal. And soil conditions may have contributed to these failures. So this is a bus filled with holiday skiers stops just short of disaster in the Hanshin Expressway. This collapse of the elevated expressway, and then soft story failure, mid-story collapse. Maybe this is due to soft story. Then 1999 Taiwan earthquake, Chiche earthquake, magnitude is 7.3 on Richter scale. There were vertical displacements reaching up to 7 meters. Around 2,400 people died. Peak ground acceleration was 1G to 1.2G, severe earthquake. Some of the damage patterns are shown here. Commercial building with soft story at the bottom. Complete collapse due to the fault line. Damage around more than 50,000 buildings suffered here, destroyed. And partially damaged, 53,000 buildings. Even one dam got damaged. Partial collapse of a buttress and the bridge deck at the mid-crest. And then damage to roads, then slope failure, landslides, so on. Structural damage, compression failure of column exposing reinforcement at the base. And here left column is embedded in lintel beam, whereas the right column is independent, undergoing local buckling here. In this photograph, you can see upper portion of the building undergone 90-degree rotation and crushed into the ground. It happened due to crushing of columns on one side at the ground story. So at one side there was crushing of columns. The column, the upper portion of the building undergone 90 degrees rotation and fell down. Then this is shear cracks, which we have observed in other earthquakes also. And causes inappropriate construction practices. The building codes require not more than 50% of the reinforcement to overlap at a single section, but we see many columns failed where 100% reinforcement overlapping took place. And then 135-degree hooks not being provided, and also the hoop spacing was too much, violation of the codes. Then this is damage in Haiti earthquake 2010. This earlier also I mentioned, one of the poor countries in the Western Hemisphere, more than 2 lakh people died. X cracking of the walls, localized damage, column shear failures, toppling and out of plane wall failures. All these kinds of damages were observed. This is the collapse of a church in Haiti. You can see the failure here at these corner portions. Then poor aggregate shape and grading, poorly located construction joints, formwork embedded in finished concrete, no proper care being taken, debris left in joints, segregation, voids, honeycombing. These are all some of the causes of failure in this earthquake. Then 2011 Tohoku, Japan earthquake. A major earthquake occurred in the Pacific Ocean off the coast of Miyagi, Japan on March 11, magnitude of 9. It was one of the largest recorded earthquake in Japan. Huge physical damage and loss of life. Total deaths were nearly 20,000 people. Another 2,559 people missing. So in this earthquake, damage was due to earthquake-induced shaking. Then tsunamis were occurred. And also there was a severe accident at the Fukushima Daiichi nuclear power plant, which was the second worst nuclear catastrophe after Chernobyl disaster in Russia. So this is Miyagi Prefecture. This is Tokyo. So this is the affected area. Building damage to site-specific ground motion. This is in Sendai city. Sendai city is here. So there is Tohoku University. This is a department of actually civil engineering, civil and architecture. 9-story building housing the departments of civil engineering and architecture in the Faculty of Engineering at Tohoku University was damaged. This building was constructed in 1969 and it was retrofitted after the 1978 earthquake. There was continuous monitoring of this building. The building was on a hill slope site and had as a foundation with reinforced concrete cross piles of length 12 meters. Sorry. The building was heavily damaged at the bottom of 4 corner columns. At the bottom of 4 corner columns, this is a closer view of those columns. There was heavy damage. And okay, these locations are shown here. And this is shear wall, reinforced concrete wall. There were cracking, damage in these shear walls also. So this kind of failure occurred in many buildings. X cracking, damage to non-structural wall, then damage to beams. Then this building, inclined 4-story RC pile foundation building, subsided bottom part of the southeast corner column. So this column has subsided. Subsidence has, ground subsidence has occurred. And uplifting of the foundation in the north side. In the other side of the building, there has been uplifting. So one side has sunk, other side has moved up. Then damages due to tsunami, concrete wall failure due to internal pressurization, uplifted and overturned 2-story RC building, then damage to fish market building. So many coastal structures and ports and harbors got damaged during this tsunami. And then nuclear disaster, as I said, nuclear power plants got affected here. Now what happened, the earthquakes caused shutdown and then the reactors electric supply failed. So they automatically started the emergency diesel generators. These provided the critical electrical power to the pumps that circulated coolant through the reactor's cores. When tsunami generated arrived shortly afterwards, it flooded the lower parts of the reactors, causing the failure of emergency generators and loss of power to the circulating pumps. They had not anticipated tsunamis of this much height. That is why they could not withstand. When the tsunami came to this region, it flooded the lower parts of the reactors and the generators failed. The resultant loss of reactor core cooling led to nuclear meltdowns, hydrogen explosions, and the release of radioactive contamination between 12th and 15th March. So some of the damaged photographs you can see. Damaged buildings at Fukushima Daiichi nuclear power plant. They are telling that no one died because of radiation, but a lot of people were evacuated from that region, and still presently also they are not permitted to return to their hometowns. This is 2015 Nepal earthquake. Epicenter magnitude 7.8. This is the epicenter. So portions of Nepal and also portions of India experienced heavy shaking. So some of the damaged photographs, this is fissures, damage to a temple here. I think the earthquake resistant design part I will skip. I had prepared some slides, but anyway, I think it will be covered in subsequent lectures. We have to make the structure as much light and as much ductile as possible. Earthquake force. Earthquake force is a function of mass into acceleration. So if a structure is, so we have to design the building as light as possible and ductile. Why is ductile? A ductile structure has ability to absorb energy without critical failure, and it allows the structure to undergo large deformation without, with little decrease in strength, and it has the ability to sway back and forth during an earthquake and to withstand the earthquake effects without collapse. The earthquake resistant features will be discussed by other speakers, so I will skip this. It's already 12 o'clock. The seismic performance, this is maybe some of you have seen how through base isolation we can reduce the effect of earthquakes. So here we have provided the base isolation. So some of the isolating devices marketed by this company are shown in this video. Various bearings like elastomeric bearing, lead rubber bearing, sliding bearing, ball and roller bearing, etc. This is one of the modern methods of controlling the earthquake-induced motion. Then in Bhuj, they have provided base isolators for a hospital building. It was damaged during Bhuj earthquake, and then it was reconstructed with the support from New Zealand government, and they provided these isolating devices. Then dampers, seismic dampers. This video shows how these provision of these dampers will help in reducing the vibration. So this is without bracings, without providing the seismic dampers. So this is with, so you can see the difference in vibrations. So this one of the photograph here, you can see how these diagonal bracings and dampers are provided to improve the earthquake behavior. So closer view of these seismic dampers in one of the buildings fitted in ES. This is in Taiwan. They're providing these lockup devices at the for the bridges. Taiwan high-speed rail, Taipei, Taiwan. 34 seismic lockup devices provided. Then another system is providing these bracings. The structural system consists of moment frames with specific base provided with braces throughout the height of the building. As you can see here, they can help in resisting both wind and earthquake loads. Braces help in reducing overall lateral displacement of buildings and in reducing bending moment and shear force demands in beams and columns of the building. This is John Hancock Center in Chicago. Then this is from Japan. This is the new technique they are trying. A Japanese textile from Komatsu Seirin recently used high tensile twine developed from carbon fiber to reinforce its facility in Nomi, Japan. They are office only. They are providing these 1,000 of these high tensile rods all around the building. And inside the showroom, another curtain of nearly 3,000 additional rods have been provided. And this is in New Zealand, cardboard used as an alternative to conventional material. The Transition Cathedral in Christchurch, New Zealand was constructed using 98 giant cardboard tubes reinforced with wooden beams. The cardboard and wood structures are extremely light and flexible. And this is the completed view here. It performs much better than concrete during seismic events. So they are trying this. This is during construction. This is final view here. So cardboard reinforced with wooden beams are tried here. You can get information from this source about this. Another is Levitating House. The airbag here, this is the building, and they are providing airbags at the bottom. When the earthquake is detected, the air is pushed in the airbags. And this is the normal view. And when there is earthquake, the airbag helps in lifting the building. The airbag lifts the house by 3 centimeters from its foundation. The structure will hover for the duration of the earthquake, and then the airbag deflates and the structure settles to its original condition. So air is pushed here. So home levitates, and then earthquake stops, home returns to the original position. This technique can be used, can be fitted to new homes of appropriate weight, and also can be used to retrofit the existing house. This is being tried as the new technology. And then this is eco-friendly ductile cementitious composite spray, EDCC. EDCC combines cement with polymer-based fibers, fly ash and other additives in making it eco-friendly. This material, when applied as a thin coating, about 10 mm thickness, was found to have improved seismic resistance of the structure by withstanding an earthquake of intensity 9 to 9.1 on Richter scale. Many buildings in Tohoku, 2011 Tohoku earthquake, they withstood, and it is said that maybe due to this EDCC spray. At present, this technique has been suggested for retrofitting of buildings like elementary schools, retrofitting of elementary schools in Canada. Lot of things to learn from the nature. This is blue mussels can be found clinging to rocks and sea decks all along the coast of New England. To stay attached to their precarious perches, mussels secret sticky fibers known as byssal threads. So these are sticky fibers or byssal threads. Some of these threads are stiff and some are very flexible. So some are stiff and rigid, some are very flexible and elastic. And now researchers are trying to incorporate these features into structures, whether we can utilize, we can learn from the nature and utilize these to make the building earthquake resistant. I think this is over. This is last slide. This last slide. This is our NITK beach. And this is a lighthouse near Surathkal. And NITK campus somewhere here at this side. About 300 acres land we are having, 295 acres. Somewhere gate is here. So we call this NITK beach. So those who have visited NITK might have seen our beach. So thank you. Thank you for your patient hearing. And if you have a chance to visit NITK, maybe after the situation improves, most welcome.
Thanks a lot, Kata sir, for the wonderful session. and invitation to your institution also. Actually, the session was very well structured and a lot of examples, case studies, equations, everything you have shown us. And we are really benefited by your session, sir. Thank you so much, sir. Participants can now ask questions to Kata, sir. You can either type questions in the chat box or you can unmute yourself and speak out.
Sorry, I took slightly more time.
Yes, sir. No problem, sir.
Good afternoon. Well, it was worth it, I suppose. Even if you overstayed the time, I think it was worth it. Okay. So can I ask a perhaps a trivial kind of question? And from a domain which is not civil engineering. Okay, I belong to electrical engineering.
Yes, madam, please.
So what we normally do with respect to some vibrations that occur with respect to some feature. Okay, of course, it happens in electrical engineering. We normally identify the dominant mode of oscillation, the eigenvalue kind of solution, and then we remove them. Is it possible in earthquake-related vibrations, or is it vibration?
Yes, madam. We do techniques. We can remove the noise and say which is the dominating frequency of earthquake, and this will help us in understanding which buildings get damaged, which building we can expect to get damaged during the earthquake. Yes, sir.
Can you add dampers based on this understanding to already built dampers, etc.? Because
for retrofitting buildings we can use also, depending on the seismicity of the region, which are the and also the natural frequency of the building. We can design the bracings, dampers, so that the earthquake resistant features will be there, or earthquake resistance characteristics are improved for the building.
Thank you. I think that could be a solution that the students can work on, isn't it?
Yes,
okay, even on as-built structures. This must be applicable to the bridges. It must be applicable to also the power power line towers.
Yes.
Okay.
Also, each earthquake will be different.
Yeah, that's right. Yeah. And the direction may also be important.
Yes.
Okay, then thank you.
We normally divide into two perpendicular directions along the building and perpendicular to the building axis, and try to analyze the effects. Yes.
Thank you, sir. It's very clear.
A lot of research in earthquake engineering is done by Central Power Research Institute in Bangalore, where they check the electrical components, how they withstood or how they withstand, or up to what exertion or what shaking those electrical components can withstand the earthquakes. We also did some collaborative research with CPRI regarding this earthquake resistant features of electrical equipments.
Thanks again.
Yeah.
Any other questions? Please type in the chat box or unmute yourself and speak out, please.
Anyway, people can ask questions later also. My mail ID is there. Always welcome.
Okay, sir. Yeah, sure.
To interact. Thank you.
Also, the slides will be shared with you all later. All the videos, recordings, everything will be provided in the YouTube link. Also in the AACT Atal link website. So if you have any queries, you can ask in the WhatsApp group or mail directly, sir, also. Please complete the feedback link, that is attendance, feedback and assessment. So please complete it before 1 p.m. today. So I hope there is no more questions for discussion right now. It's already 12:50. We are 15 minutes late for next session. Anyway, we'll wind up now for lunch break, and we'll continue with our second session starting from 12:45. So once again, thank you, sir. Thank you.
Thank you, madam. Thanks for
Thank you from the bottom of our hearts. Thank you so much, sir.
I will leave.
Yes, sir. Thank you. Yeah, thank you, sir. So thank you all. You can join back by 12:45 p.m. Once again, please fill the feedback form now itself. Thank you all.
Hello.
Yes,
Hello,
sir.
Abhilasha.
Yes, sir.
Can
Yes,
I-
sir. Yeah,
Sir?
definitely, sir. Definitely, sir.
So I'll come at 12:40. Is that okay?
Pardon, sir?
I shall be ready. In fact, I'm ready all the time. But I
Okay, sir.
come
Okay.
at
So
12:40 is okay. 12:40 is fine. So
Yeah, yeah. Oh, okay.
the slides are elementary theory and vibration. That's the first one, and then calculus PDF. These are the two things.
Okay, sir. Okay, okay. I'll share it
And
from
then
here, sir.
yeah, and you
I'll
can
share-
give the questions after that session.
Yes, sir. Yeah. Questions
So,
will be given at
that,
the end of session, sir.
yes. So we will start at 12:40 or so, and then you can show the elementary vibration theory, and
Okay.
and there
Okay.
we can we'll talk about that. At that 1 minute clip, I will tell you when. Hello. Hello.
Hello. Yes, sir. Yeah.
Yes.
Sir.
Can you hear me? Yes.
Yes, sir. Yes, sir. Yes, sir.
So I'm on camera now. Yes. So let's start the introduction, and we shall begin our business now.
Okay, sir. We shall start now, sir. Let me share my screen.
Begin with the introduction and elementary vibration.
Okay, sir. Okay. First one is vibration, right, sir?
Yes, elementary vibration theory.
Okay, sir. Okay. Okay, sir. Now only 42 participants joined here. Let's wait for just 1 more minute, sir.
Okay. Well, you can maybe give the introduction and then introduce the speaker, and then by then people will join. Otherwise,
okay, sir. We'll start. Yeah. So very good afternoon, one and all present over here. So our next session is vibration of continuous systems, and it is handled by Dr. KBM Maheshwaran Namboodiripad, Professor, NIT Calicut. He's retired from NIT Calicut, and he did his BSc Engineering Mechanical from Kerala University in 1960 and MTech from IIT Kharagpur in 1963. He did his PhD in Engineering Mechanics from University of Saskatchewan, Canada in 1971. And he worked in NIT Calicut from 1964 to 2002 as in various posts, lecturer, assistant professor, professor. Then after that, he worked as Dean in Amrita Vishwavidyapeetham, Ettimadai from 2003 to 2004, and as Dean in the same campus from 2004 to 2010. And he also worked as part-time visiting professor at Amrita from 2010 to 2016, and part-time visiting professor at our own institution, that is Vidya Academy of Science and Technology, from 2010 to 2020. He's still continuing with us, and he worked as guest professor at the University of Basra, Iraq, guest professor at the University of Karlsruhe, Germany, 1999 to 2000, and short-term guest professor at the University of Concordia, Montreal, and short-term researcher at the University of Pavia, Italy. And he delivered many invited lectures, both in India and abroad, in many countries like Germany, Canada, France, Italy, Singapore, Bulgaria, Sweden, etc. He has several research papers and 2 patents and 5 technical books. He's a consultant for vibration, stress analysis, and general mechanical engineering. We welcome you, sir, to the second session of our FDP. Warm welcome, sir.
Thank you. Thank you.
Yes, sir.
Hello?
Yes, sir.
you
You
hear
are
me?
audible, sir. Yes, sir. You are audible, sir.
Yeah. Thank you for the introduction, warm introductory note. Good afternoon, all the participants. Very good afternoon. I'm here to give you some idea about the underlying vibration theory, which is so important in the context of earthquake engineering. I plan to give you first a few basic concepts, then the single degree of freedom system, and then free undamped vibration, natural frequency, free damped vibration, forced vibration, resonance, and so on. So this is at a very, very elementary level, because I'm not sure how far civil engineering students would have learned vibration theory. It is very important to understand some simple concepts, and from the simple concepts, we can build further on multi-degree freedom systems and continuous vibration system. Actually, to discuss vibration in the context of engineering, earthquakes, we need to go into advanced theory, but we cannot do that because the background of the various listeners will be naturally different, and I would rather like to be elementary, deal with it at a very elementary level. So let's talk about every system. Next slide, please, Abhilasha. Next slide.
Yes, sir. Yes, sir.
Next slide.
Okay, sir.
Next slide. Every system having mass and elasticity is capable of vibration. Therefore, mass and elasticity, that is M and K is a spring constant. These are the 2 parameters of greatest importance in a vibration system. Occasionally, energy dissipation also is important. If that is the case, damping also is a factor. Thus, mass M, elasticity springiness K, spring constant, C, damping constant, are the most important elements of a vibration system. We shall first talk about a single degree freedom system. The external frequency is called, well, undamped natural frequency is omega is equal to k by root of k by m. Sorry, I forgot the square root of k by m. Damped natural frequency omega d is omega into 1 minus zeta squared, where zeta is the damping ratio, which is the actual damping divided by the critical damping. Usually zeta is very, very small. It's of the order of 0.05, 0.02, etc. So which means that omega d is almost the same as omega n. What does it mean? It means that if your interest is the calculation of natural frequency, we can afford to neglect damping, because damping has practically no role at all in the calculation of the natural frequency. That's now, if damping is usually very small, that's of the order of 0.02, etc., which means omega d is 0.999 times omega n. So there's no difference between omega n and omega d. Theoretically, omega d is slightly, ever so slightly less than omega n. So omega d is almost the same as omega n. Let's go to the next one. Now there is an external frequency, which is called omega. And if the natural frequency happens to coincide with the, if the external frequency omega happens to coincide with the natural frequency, then you have the state of resonance. Resonance means the amplitude of vibration is very large, and amplitude of vibration builds up and then reaches very high, often dangerously high amplitudes. Thus, if omega is close to omega n, danger, avoid this. So a great deal of vibration analysis is to make sure that the danger of resonance is avoided. In only rare cases, you have resonance is desirable. For example, if you are designing a vibrator, where the purpose is they must vibrate, except in these rare exceptional cases, resonance must be avoided. So if omega is close to omega n, there is danger, and avoid this. That's what you're talking about. So the whole of vibration analysis can be put in a nutshell. Calculate omega in natural frequency. Calculate omega. If they are equal or nearly equal, then there is a possibility of resonance. Then that must be avoided. How can you avoid that? Change omega if possible. External frequency. How do you do that? If it's a rotating equipment, try to see whether you can run it at a different speed. But sometimes it is not possible. You have, it may be a synchronous machine. It can run only at a specific speed. So in such cases where it is impossible to change the external forcing frequency omega, then you have to change omega n so that resonance can be avoided. In some cases, as the case of automobile engines, the engine has to run at different speeds. So resonance cannot be avoided. So why is this impossible? Because the engine is a variable speed engine, and as in the morning when you start the engine starts from rest and it goes to some 4,000 RPM or something like this. As it goes from 0 to 4,000, it passes through these natural frequencies. There are several natural frequencies. So therefore, don't stay at any natural frequency. If you do that, if you stay there, then the amplitude of vibration rises and rises and rises, and it is very, very dangerously high. So avoid that. So the idea is only very, very simple. If omega is close to omega n, there is danger. Avoid that. How do you avoid that? By changing omega, the running speed, if that is possible. If that is not possible, change omega. How do you change omega? Root of k by m. Change mass, change k. Mass cannot be changed because you cannot have a very, very large mass. It becomes very, very unwieldy. It's theoretically possible, but actually it is not possible because you cannot change the mass. You cannot have a huge, great big, huge mass. That's not possible. So the possibility is to change the spring constant. How do you do that? By changing the support conditions, etc., etc. The idea is this. Here is a physical problem. The physical problem has these three parameters: mass, elasticity, which is spring constant. These are the two important things. And sometimes it is important to calculate the energy dissipation. Then, and then alone, you need to consider damping C. So M, K, and C are known as the parameters of a vibration system. Now, during operation, you have an external frequency, omega. So you have the natural frequency, omega n, and the external frequency, omega. We must make sure that omega is not very close to omega n. Because why? If they are equal, then there will be resonance. If there is resonance, resonance leads to very high amplitudes, and either the structure comes crashing down, or if you are fortunate, it may not actually crash, it may not fail, but the running will be very rough. So that's how it is. So if resonance cannot be avoided, operate only beyond the dangerous reading and introduce some damping. So this is all that you have to know about vibration theory. That's all. Now, if you see advanced books on vibration theory, generally discuss the various methods to calculate omega n, natural frequency. After calculating omega n, what do you do? Well, this is what you do. Check whether it is very close to omega. If it is so, there is a possibility of resonance. It represents danger. Avoid that. By what are the ways? Changing the operating frequency by running the engine at different speeds, etc. If that is not possible, sometimes you cannot change, you have restrictions. Then if that is not possible, then change the natural frequency. How do you change the natural frequency? By changing the support conditions. You can mount it on soft springs. If you mount it on soft spring, the natural frequency comes down. If you mount it on stiff springs, the natural frequency goes up. So whatever you do. And sometimes you cannot avoid resonance. Then what do you do? What do you do? Restrict the dangerous amplitude to some safe limit by introducing damping. That's how it is. So here is a figure, damped natural frequency. The spring the parameter m d2x by dt2 plus kx equal to 0. That is the equation of motion of this single degree freedom system. And its solution, you know, is x equal to xt. X is the displacement from in this vertical position, it moves up and down. So x as a function of time is a cos omega n t plus b sin omega t. Omega n is a natural frequency. Omega n is equal to root of k by m. I'm sorry for the omission. There should be a square root. Omega n is equal to root of k by m, undamped natural frequency. Now, you have a free damped vibration. Sometimes it is important to introduce damping. Why? Because there is some energy dissipation, or you need some energy dissipation. You have a pendulum that keeps on oscillating back and forth and back and forth and back and forth. So if there is no damping at all, it will continue to oscillate. But it doesn't happen. You know that there is some resistance. So take into account all that, then you have this C dx by dt. So m d2x by dt2 plus C dx by dt plus kx equal to 0. The solution is e raised to minus zeta t into a cos omega dt plus b sin omega t. The damped natural frequency omega d is omega n into root of 1 minus zeta squared. Square root of, I left out square root of. Now you have a forced vibration. What if the system is acted upon by an external load? Ft sin omega t. Look at the differential equation. M d2x by dt2 plus next slide, please, Abhilasha. Next slide, please. Yeah, that's right. That's right. M d2x by dt2 plus C dx by dt plus kx equal to ft sin omega t. I'm sure you have all studied this. So this is no more than a quick review of what you are supposed to have studied this. Without knowing this, it is not possible to discuss vibration theory. So this xt, now it is made up of two parts, complementary function and the particular integral. The xt is the steady state amplitude, and we are talking about steady state amplitude. Now, you have a vibration isolation. Next figure, please. Next one. Next one. Next one. Next. There's no next. There is a one vibration. One more. I think one more. No. Yes, there's vibration isolation. Yes. So what happens is, you see here, vibration isolation. There is a spring mass system, and there is an external force F, and there is an unbalanced force. If it's a rotating machinery, the unbalanced force, if the rotor is unbalanced, you will be transmitting to the foundation the unbalanced force. That will create problems. So the right way to do this is to isolate the vibration. What does it mean? It means the force to be transmitted to the foundation must be reduced. Or how shall we do that? What we do is, we try to balance the rotating machinery, because it is unbalanced force which causes the force to be transmitted to the foundation. Therefore, try to balance the rotating mass so that the unbalanced force is zero. And now mount this on soft springs. If you mount it on soft springs, you find that the load that is transmitted to the foundation becomes very, very small. So the mass, the machinery should not be bolted down very, very heavily. It should be mounted on soft bearings. So you feel uneasy. It should be mounted on soft springs. It may dance about a little bit here and there, so you feel a little uneasy. I'll come to that later. So this is the basic theory. So look at this. The force vibration isolation. The force transmitted is K into the displacement. The spring force into the displacement. If this is to be kept low, we must operate at the far right of this figure. At the far right means omega by omega n should be very large. Thus, the body must be mounted on soft springs. Now, what happens is that there are psychological aspects. How do you, what is psychological aspect? When I was a young student in IIT Kharagpur, we had taken 2 courses on machine vibrations. And as part of this, I was reading this book called Macduff and Carreri, which is called Vibration Control. He talks about this vibration isolation and then says that psychological factors prevent the use of this. I was 23 or 24, 23 perhaps. I was as sure as a young lawyer. And I said, vibration theory has nothing to do with psychology. I was absolutely sure, as sure as a young lawyer. I was bouncing with enthusiasm. I said, no, there is no way vibration theory has any psychology in this. And then what happened was, I left that. Other priorities came into our life. And then years later, I got a call from the nearby industry. There is a platform. And on the platform, there is a rotating motor. And this platform was vibrating violently. You feel that all hell has broken loose. The vice president, Mr. Kuchikrishnan, called me. He said, "Namboodiripad, come here. And we are sending you the car right away. Come right away." I had just got up. He said, no, you're going to have your bath all that later. Now come right away. So I'm sitting in the car. So I came there. And then when I went there, the platform was vibrating violently. I inspected this and found that this is because of the unbalance in the rotating machinery. I said, can you change the speed? He said, no, you cannot change the speed. Why? Because this has to supply air to the boiler. And you cannot change that. So can you balance it? We can, but it would mean you have to stop the machinery. And if you stop this machinery, it takes a long time to start again. So it will cost the company millions of rupees. So we don't want to stop that at all. Then I said, mount it on soft springs. Then Kochi said, well, Dr. Namboodiripad, you may know your mathematics. Well, and he was so you see, when you tighten the bolts and make everything pakka, you feel you're secure. Actually, here the correct solution is to mount it on soft springs. When you mount it on soft spring, the mass does not sit it dangles here and there. So you feel it is not secure. He will not. He would. Quotation will not agree. He said, "Well, doctor, I know you may be good in your mathematics. You may be good in your mathematics." What it meant was, I'm not willing to accept that. Suddenly, I remembered. Yes, Macduff and Carreri, psychological aspects. The psychological aspects prevent you from using some of these things. So our in practice, as a vibration consultant, the best solution, the technically correct solution, is often not possible for various reasons. For example, in this place, the correct thing is to remove the motor, balance it, and mount it on soft springs. That's the correct solution. But they will not accept that. So you have to do something else. That is why psychological aspects. So if my student does this, my student does what I did myself, he will not pass. He will fail. He will get a D grade. He will not even get a C grade. He will fail. But you are forced to do certain things because that is the only thing which is acceptable to the customer. After all, you are a consultant and your interest is to serve the client. The client will not accept this. So suddenly I remembered Macduff and Carreri, psychological aspects. So it prevents you from implementing technically correct solution. Now, can you go first few slides before, please? Please, next slide. Abhilasha.
Yes, sir.
Next slide. Yes, no, next one. Next one. Yes, that's it. No, no, not that. Next.
Before this.
This one. Right. This is okay, yes. Now here, this is a ground level. This is a stone crusher unit. Stone crusher. The stone crusher crushes stone, and it creates a lot of noise and vibration. What happened to us? You see, at the far right, there's a house. This noise and vibration travel through the ground and causes vibration there. The people living in their house cannot eat their dinner properly because the dining table shakes. That's a problem. So this happened about 6 months ago or so. So the owner got in touch with a friend of mine. He happened to be my former student. So he thought I would be able to solve this problem. So he came along and they said, "Can you come?" So I said, "Yes, I shall come." So what happened was, again, the technically correct solution is to balance it and to mount it on soft springs. But it will cost a lot of time, and they will have to spend a lot of money. So they would not do that. So what I suggested was, you see, you can see the noise and vibration traveling through the ground to the next building. So you have a trench, and break the path, one or two, and have some trench and fill it up with loose soil or vegetation, whatever it is, and then on in the household, you ask them to keep the legs on some neoprene pads or some kind of soft spring, some kind of damper sort of thing, some rubber pads. So that's it. The problem was solved there. So this is not a technically correct solution. The correct solution is to balance it and then to have vibration isolation. but that will be too expensive. These are all, they are all small scale sort of people. They will somehow get this from some people. These are not properly designed. They don't have a vibration consultant. They have no idea at all. They simply take some design from somewhere and then try to build it there, and all kinds of funny things happen. That's it. So very often what happens is, in a practical, as a practical vibration consultant, you have to make sacrifices, you have to make compromises, because what is technically correct can be expensive, can be time consuming, and it will not be acceptable to the client. After all, you are a consultant for the client. Whatever is acceptable to the client only is possible. So that's it. So that is the first part. Now, I just want to make sure that I hope my listeners are all familiar with this single degree vibration system, MX2 dot. So with this, we can have the basis for studying higher things. Most problems require only very elementary theory for its successful solution. I once had an opportunity at an international conference. The real doyen vibration, J.P. Den Hartog, was a professor. He had already retired from MIT. He was a main speaker. He spoke for 90 minutes. Beautiful lecture, beautiful, very humorous, Den Hartog. And then he was taking rest. So he was my hero from my Kharagpur days, student days. I went up to him and then started talking to him informally. Then he said, he told me this, straight from the horse's mouth. Most problems require only very elementary theory. And then he said, otherwise, I will not be able to solve them at my age. I don't think that part is true. He may have said this out of humility. But so I'm just quoting this on the testimony of no less a person than Jacob Peter Den Hartog, JP Den Hartog, my hero. That's it. Now, what happens is, if you have a machine running on a shaft, and then you find that it runs at a dangerous speed, resonance. So what do? There's a critical speed. The speed must be reduced or increased, or reduced or increased. So you will measure the natural frequency and then check, and then you find that if it is resonance, slightly change the diameter. What happens is, if you slightly, ever so slightly, the deflection changes drastically. Why? Because the deflection is d raised to 4. You see, it is, if the deflection is, if the diameter is changed by 5%, the deflection changes by as much as 4 times, because it is a 4th root. So slightly reduce the diameter, then the natural frequency will come down drastically. So you will take much away from the resonant frequency, and most always it is the problem can be solved. In fact, in the early days, before Den Hartog was established as a successful vibration consultant, a little later he was accepted as the real ustad. So if he says something, nobody will challenge them. But in the early days, before he had established himself, the young engineers were very unhappy. He said, already the machine is dangerous at this time. You want to make it weaker by reducing the diameter? They wouldn't agree. But then Hartog said, no, on my responsibility, reduce the diameter by 1/8 of an inch, US, so it's inch units. So they did that very, very reluctantly. But then, lo and behold, the problem was solved. That's it. The problem was solved. Never again they had problems with that vibration problem. So very often, vibration problems can be solved with the knowledge of a very, very elementary theory. And I request that teachers, some of you are probably teachers, make sure that the students are given some exposure to live practical problems in vibration theory. And only if you do this, you will have the confidence. So most unfortunate part of it is most teachers have no idea at all of the industrial situation. Unless teachers are here to solve problems that face the industry. Unless teachers have first-hand experience of what happens in industry, we will not be able to be of help to them. Our statements will not have the ring of truth. So I request my young teachers, one, to understand the theory, elementary theory, very, very well, absolutely, without any shade of doubt. And then you can see how they can be applied to various situations. There are only these little things. Natural frequency should not be too close to the operating frequency. That's all, nothing else. So now you do whatever is possible. And I think it will be nice to see some examples, actual real experience, and try to see how these problems can be translated in terms of vibration problem. I'll tell you another problem. There is a vibration of a torsional vibration of a helicopter wing. On analysis, this is again the problem. So the right way is to make sure that the unbalanced torque is not passed on. You see, this is an electric motor. Electric motor, if the frequency is supply is omega frequency, the torque has twice the frequency. If omega is the our AC, the frequency is 50 hertz. The torque varies. If you remember your electrical engineering, I remember my electrical engineering, we had a wonderful teacher, so he taught us that. So the torque is proportional to twice the frequency. So the torque will have 2 times the natural frequency, which means 2 times omega, which means 100 hertz. So now this is the offending thing, and you have to identify this and then have some proper vibration isolation. This was the problem. Now, I had the opportunity to get, there is a vibration engineer, I remember his Narayan Rao, his name was Narayan Rao. He was an engineer in HAL. So we invited him, and he took two days, about 5 + 5, 10 hours of lecture to tell us how they were able to diagnose the problem, and having diagnosed, how they were able to find an effective solution. And I was so much impressed by this that I requested him to visit us again and again, but he was so busy and it was not possible. So I think it is necessary for engineers to invite people from industry, make sure that they understand their problems clearly and try to learn these problems, 1, 2, 3, 4, 5, about 20 problems, industrially important problems, and give this as a very, very important component to their theory classes. Unless we expose our students to industrial problems, no engineering education will succeed. And one of the reasons why engineering students do so badly is because they have no exposure at all. How can they have? The teachers themselves do not have any idea of, they themselves have no exposure to industry. So this situation must change. I think most of my listeners, I hope, are young engineering teachers, and I request you to make sure that you use your influence and make sure that industrial the teachers are given sufficient industrial exposure. Let me stop here for a few minutes, and then if you have some questions to ask, I shall be glad to answer. But the answer will be, I do not know. We shall together examine. So I'll stop here for a few minutes, and then we will continue from there.
Okay, sir.
Participants? So, go back and then come to a multi-degree Fernando system. Go higher up in this.
Okay, sir. So participants, please ask your questions in the chat box. You can either type down in the chat box or you can even unmute and ask questions directly to sir.
Yes, that's it. No, next, go back. That horizontal business multi-degree freedom system. Next slide, next slide, next slide, next. Before that, before that, yes, that's it. No, that horizontal thing. That horizontal one, horizontal with several masses. Next one. Next. Yes. No, previous one. Previous one. N degrees of freedom system. N degrees of freedom. Previous one.
Yes, sir. Yeah. N degrees of freedom.
Previous one. Yes, that's it.
Okay, sir.
I'll wait for another 50 seconds or 20 seconds and then start.
Okay, sir.
Now, when you have multi-degree freedom system, N degrees of freedom. So what does it mean? It means there are N independent, there are N masses. So 1, 2, 3, 4, N. So for each mass, you have a differential equation of motion. So if this N degree freedom system is governed by N differential equations. You see the first one, second equation, third equation, fourth equation, etc. So there are N equations. And so there are a set of N differential equations. They are have to be solved. You cannot solve them one at a time, because the first equation, which is the equation of motion for the first mass, includes not only x1 but also x2. Second one includes not only x2 but x1 and x3. So you find these are all coupled equations. They are all coupled equations. You cannot solve them one at a time. Oh yes. Here's the question: how do you see when you cut a trench, you're eliminating the path for the vibration, unbalanced vibration and acoustics sound to travel. So that's why you cut a trench and fill it with loose soil and maybe some kind of vegetation and some creeper or something. Then you can do that. And the way to deal with acoustics is you can have slightly the building, the two walls should not be parallel. Then what happens is there will be echo and reverberation. So make sure that the walls are slightly inclined so that they will not there will not be any vibration, reverberation or echo. So, and then have some kind of plants there. If you don't do that, what happens is the workers there will have serious hearing problems, because they are exposed to a high level of noise. They will have permanent hearing problems. So make sure that the two walls are not really parallel, but slightly at an angle, so that the noise will not be reflected and the same place. That's one thing. Secondly, have some kind of rags, some torn cloth or some creeper, etc., so that the acoustics are all absorbed there. And because you see what happens is there are acoustic absorbers, but they are all very expensive. And these little small scale people cannot afford to have, cannot afford to spend 20 lakhs, 50 lakhs, etc., to improve their plant, because they are operating at a very, very low 5 lakhs. Even 5 lakhs is a lot of money for them. So 2 lakhs, 1 lakh, it's even that they are not willing to spend. They cannot afford to spend. So you can do some of these tricks. And then, of course, make sure that this noise is not carried to the house. How do you do that? Have some kind of shrubs, have some kind of vegetation, have a vegetable garden there, so that when there is thick growth, then that will be absorbed. Noise will not be, acoustics will not be passed on to the house. Exactly the same way, if you cut a trench, have 2 trenches if possible, and then that will not be possible. And besides, by way of abundant caution, have some kind of rubber mount the table of the dining table, legs of the table on soft rubber pads. That will solve the problem. Okay, is that clear, Mr. Santosh, Professor Santosh? Is that clear? Did I answer your question? Okay, okay, thank you. Thank you. So now, here, sometimes you have several natural frequencies, not just one. For example, try open in the morning, start your engine, open the bonnet and start your engine, car engine, and take it to the full speed, and then shut down and watch what happens. Is as the speed goes up, the speed starts from 0 to about 4,000 RPM. As the speed falls from 4,000 to 3,800, 3,600, 3,500, the whole starts shaking. What's happening? Probably it's going through a natural frequency. So maybe 3,300 is the natural frequency. When the speed falls below that, again, there is no vibration. Then when it slows down further at about 2,600 or so, again, it starts shaking. After some time, vibration stops. Again at 1,400 or so, again it starts vibrating. What happens is this engine is mounted on springs. So the engine assembly has several natural frequencies. When the speed is changed from 0 to 4,000, it goes through all these natural frequencies, not just one natural frequency, omega 1, omega 2, omega 3, omega 4, etc. It has, technically, it has infinite natural frequencies. But we are interested only in 1, 2, 3, 4, or 5, not too many. So you can see this. You raise the engine to that speed and shut down and allow the speed to fall down. And as the speed falls down, you will find it passes through the natural frequency. The whole suspension starts shaking like a malarial fever patient. And then speed 3,300, then nothing at all. Then again it starts shaking, then nothing at all. Then again it starts shaking. It will be nice if you can go home and try to do this. And you can see this. It is said that seeing is believing. If you see this, you can see. And that is what happens is, as the speed falls from, what's harm in speed going up? Because the speed goes up very, very fast. And it's not a good idea to stay at the resonant speed. There will be a danger. So take it up to 4,000 RPM or so, and then stop, shut down the engine, allow the engine to slow down for 4,000, 3,800, 3,600, 3,500, 3,300, it starts shaking. And then about 3,000 again it stops, etc., etc. So now here there are n natural frequencies. So if there are 4 natural frequencies that you're talking about, you have to model this as a 4-degree freedom system. How many degrees of freedom does it have? Actually, every system has infinite natural frequencies, but it is not possible to set up complicated equations and solve them and then incorporate them. So very often you have to use our engineering judgment and try to see how you can simplify this system. So you make simplifying assumptions. Actually, all systems are nonlinear. Linearity is only a small part of nonlinear systems. So in fact, the famous vibration consultant, vibration theory, he said, dividing equations, differential equations into linear and nonlinear equations is like dividing all the things in the universe into bananas and non-bananas. So classifying differential equations into linear differential equations and nonlinear differential equations is like dividing all the things in the universe into bananas and non-bananas. Poor bananas have no chance at all. Non-bananas. So similarly, nonlinear differential equations are many more than linear equations. But what happens is nonlinear differential equations are extremely difficult. Its theory is not known properly, and we cannot solve them easily. So very often, linearity is a simplifying assumption. We might have to make simplifications. So linear, you assume that everything is linear, so that you know linear theory is well understood. You know, even without solving the equation, you can know the nature of the solution. You see, it's like this. Sometimes it is sufficient to know the nature of solution. You don't have to solve the equation actually. So the nature of solution can be found out even without solving the problem. I'm fond of saying this to my students. A young white woman marries a black American, what we call Negro. Negro is not a politically acceptable word, so you say black African. So a white girl is married to a black American. What kind of child will they have? To answer this question, you need not wait until they marry, beget a child. And what's the child? You know that the Negro characteristics are very, very strong. The child will be like his father, not like his mother. So sometimes you don't need to solve the equation. It is sufficient to know the nature of solution. So because what's the problem? The problem is the equations are generally very, very difficult. Nonlinear equations are sometimes very difficult. So there are methods by which you can infer the nature of the solution without actually solving them. So I'm just passing on these things, assuming that my listeners are teachers and they know all these things. So I do not want to tell you things which you can see readily from a book. I would rather like to supplement this by my insights or my explanation, which you may not see in other books or anywhere, for example. It is in my head and nobody else's. I want to make sure that my lecture is my own, not anybody else's. Nobody else. Somebody may be able to teach better, but nobody can teach it. It's my way. This is my way. So I'm giving you my insights, my stories, my explanations, my insights, whatever. Not go through the detailed solution. The detailed solution you may have already studied, or you can see them from any book. So here are n masses. So there are given by n natural frequency, n differential equations, all linear, but coupled. You cannot solve one at a time. They must be solved together. They are all coupled equations. The first equation contains not only x1 but also x2. Second equation contains not only x2 but x1 and x3, and so on and so on and so on. So now what you do is, we know that the vibration is sinusoidal. So assume that x1 is equal to a1 sine omega t, x2 is equal to a2 sine omega t. By substituting over here, the differential equation can be converted into algebraic equations. So algebraic equations. So you get n differential equations will be converted into n algebraic equations, a1, a2, a3, an, the amplitudes, and the unknown frequency omega. So this is what is called an eigenvalue problem. Ax equal to lambda x. So Ax equal to omega squared into x. So you find this is an eigenvalue problem. Also, a vibration problem is always can be posed as an eigenvalue problem. Why do you want to do that? Because then you will get a lot of insights. You see, these eigenvalue problems have many similarities. All eigenvalue problems are very, very similar mathematically. Physically, a vibration problem and the problem of finding out the principal stresses, they're all similar. They're all eigenvalue problems. So for example, the eigenvectors corresponding to distinct eigenvalues are mutually orthogonal. So here also you find that the eigenvectors are mutually orthogonal. That is known as Rayleigh's principle of orthogonality. We'll come to that. Next slide, please, Abhilasha. Next slide. Yes. These are the modes. So you see, these are the eigenvectors. First mode, second mode, third mode, fourth mode, etc. These are the natural frequencies: omega 1 squared, omega 2 squared, omega 3 squared, etc., etc. And corresponding to that, these are the frequencies: omega 1, omega 2, etc. Corresponding to that, these are the amplitudes. This is called the eigenvector. This is an eigenvector corresponding to their eigenvalue. The eigenvectors correspond to two distinct eigenvalues will be mutually orthogonal. For example, the first one, A1 into A1 plus A2 into A2 plus A3 into A3 will be always zero. So A3 into A4, you multiply them, dot product, take the dot product, and then you will find it's always zero. That is known as the this is a demonstration of the simple idea that eigenvectors corresponding to distinct eigenvalues will be mutually orthogonal. And in vibration theory, this orthogonality is named after Rayleigh's principle of orthogonality. This is very, very useful, both from a practical point of view and also from a theory point of view. If you want to calculate these things at every stage, you'll find if you want to solve problems approximately, etc., you can try approximately assume something and then revise, then you will get a better approximation. But what happens is, if there is a trace of first harmonic, this will converge only to the first harmonic. So when you go to the second harmonic, what happens is, every iteration, you must use orthogonality principle and remove the first harmonic contamination, what is called contamination. Then only, I am saying like this, assuming that you have all studied this vibration theory. Without having studied vibration theory, it is not possible to know anything about our earthquake vibration. So this is a natural frequencies and the corresponding eigenvectors. I repeat, the eigenvectors corresponding to distinct eigenvalues are mutually orthogonal. That is the Rayleigh's principle of orthogonality. Next one, please. Next one. Next one. I'll give you a simple example. Here is a very simple case. Here is a 2-degree freedom system. M1, K1, M2, K2. Just for simplicity, both are equal. M1 equal to M2, K1 equal to K3, etc. So you find that the mode shape. Next picture, please. Next picture. Next picture. Next slide. These are the eigenvalues. These are the two modes. Root of K by M, root of how much is that? Root of 2K by M, and these are the 1, 1, 1 minus 1. Please see the picture corresponding to the picture. There's a figure. No, next one. Figure. Yes, that's one. Yes, look at that. The first one is the first mode. The two amplitudes, A1 and A2 are the same. And in the second mode, A1 and A2 are negative. So this is the 2 degrees of freedom system. This is the first mode. The second one is right side is a second mode. So you find A1 and 1 and minus 1. This is A1 and A2. A1, 1, 1, 1 minus 1. You see that 1 into 1 plus 1 into minus 1 equal to 0. That is what I mean by orthogonality. Look at the first mode, second mode. Eigenvectors corresponding to the two modes. Then you say 1 into 1 plus 1 into minus 1 equal to 0. That is the orthogonality. And you can see one interesting thing. Here, K1 equal to K2. So the top one and the bottom one are identical. The displacements are identical. Your displacements are identical. What does it mean? It means that the middle spring is not stretched at all. Middle spring is not stretched at all. So if the middle spring is not attached at all, then you can see A1 is the same as A2, which means they are in phase. They are in phase. They move in phase, which means the middle spring is not stretched or compressed. if the middle spring is not stretched or compressed, we might as well remove them. And then the 2-degree freedom system will split into 2 identical single-degree freedom system. So what happens is root of K by M. So the natural frequency will be root of K by M. In the second case, the 2 masses will be moving in phase opposition. When they are in phase opposition, when the bottom, when the top mass comes down, the bottom one goes up. When the top one moves up, the bottom one comes down. So you see there is, because of symmetry, anti-symmetry, you find the middle point of the spring, the middle spring will not stretch at all. So you can cut it up into 2 parts. First part, first full spring and the bottom half spring. And the second will be the top half spring and the bottom. You look at that, cut up, the other one, the previous picture. Yes. Look at that. Yes. Look at that. The first mode, the middle spring is not stretched or compressed because they both are in phase. X1 and X2, A1 and A2 are both equal. So the middle spring is not stretched or compressed, which means it is not operational at all. You can also remove them. And then what happens? The 2-degree freedom system falls apart into 2 separate single-degree freedom system, and they're identical. And the root will be, the natural frequency will be root of K by M. The second case, what happens is they are moving in phase opposition. So the middle spring is stretched and compressed, but the middle point does not move at all. That is what is called a node, having no displacement. So again, the system breaks up into 2 separate single-degree freedom system, each of K. Half the spring will have twice the natural frequency. So K1 plus 2K2, the root of 3K. That's how you get the natural frequencies. Yes. Is that clear? Now, one more thing. Now, any displacement, any vibratory displacement, let us say 3-1, can be a superposition of these eigenvalues. 1, 1, 1, and 1 minus 1. These are the 2 vectors. Any vector can be written as a linear combination of these 2 vectors. Now, this is the same thing as any arbitrary vector can be expanded in terms of the eigenvectors. So these are all very, very important. The total motion is a mixture, is a linear combination of these eigenvectors. So to find out the total motion, you find out the various natural frequency, find out the various eigenvectors, and then have superposition. C1 into the first one plus C2 into X2, etc., etc. So this is known as the expansion of an arbitrary displacement in terms of the eigenfunction. This is known as the eigenfunction expansion. If you learn linear algebra, then you learn in linear algebra, you will learn eigenvalue problems. You can see the expansion of a total vector can be written, an arbitrary vector can be written as a linear combination of these eigenvectors. In other words, it's an expansion in terms of eigenfactor. Exactly the same thing is true for n degrees of freedom system, also for multi-degree freedom system. What happens is, if there are n is increased to infinity, n differential equations will become one partial differential equation. One partial differential equation is equivalent to infinite ordinary differential equations. So what happens is this partial differential equation is equivalent to infinite natural frequency. There are, instead of eigenvectors, you have eigenfunctions. Eigenvectors, you have eigenfunctions. Eigenvalues are eigenfunctions. So eigenvalues are eigenfunctions. And again, the general displacement can be written as a linear combination of these eigenfunctions. So that's an eigenfunction expansion. These are all very, very important. I do not know how well people learn this. I am very disappointed. I think engineering college students, although linear algebra is a very, very crucial subject, it is very sadly neglected. All students do not learn them at all. They learn mathematics, but they do not see any relationship with that to engineering. So I think, in my opinion, there's a strong case for engineers to teach mathematics. I think because the mathematics teachers will not give these physical examples. So the best thing will be for the engineer teachers. Engineer teachers would have normally learned mathematics very well. Some of them will have some taste for mathematics. So you learn mathematics and try to give them the spirit of this. I myself learned mathematics the very bad way in my undergraduate classes. It is only later that I learned this, and I myself taught myself mathematics. And late in life, I learned mathematics and tried to teach wherever possible mathematics to my students. I teach the necessary linear algebra, partial differential equations, ordinary differential equations, whatever, whenever is needed. I teach them myself because I am not happy about the way it is done by the traditional mathematics teacher. And I know that I have a good company. In the early days, the industrial science, the aeronautics department, Professor Krishnaswamy, he always said, we don't want our students to be taught by mathematicians. And he used to teach mathematics himself because he was not happy about the way mathematics teachers traditionally teach them with no idea of the applications, etc. So I request some of my listeners, the ones who are mathematically inclined, to learn and invest some time and energy. And there are excellent books on applied mathematics and so on, particularly applied mathematics. A little bit of pure mathematics also will help, but pure mathematics is slightly harder, but it is good to learn a little theory is always desirable. So you see, my purpose in giving these lectures is not to teach you vibration theory in the way in which this was taught to us in our undergraduate classes. Everything is, from my point of view, my lecture is only an excuse for me to tell you my academic convictions and to persuade you to think along the lines I suggest. In other words, my idea is to convert you to my way of academic conviction. I think it's necessary, a certain amount of academic conviction is necessary. With age, many of you may be young, so you can mature slowly over the next. So what you can do is, when I was young, I was very ambitious. I had my Kharagpur studies and I was just bustling with energy and enthusiasm. So I had my training in HAL, Hindustan Aeronautics. I had my training in vibration section of that supersonic aircraft, HF-24, that was being developed at that time. So I myself did some calculations on the natural frequency of the first supersonic aircraft. And then, so I used to meet, I stayed in Indian Science hostel. And then during I used to visit these Industrial Science departments. So these renowned professors, I wanted to meet them, to see them. So he said, "Young man, what can I do for you?" Then they said, "No, there's nothing that I want to know. I would like to come here and get your suggestions, etc." Then he said, "I took 15 years to learn mathematics." He was an engineer. He was an aeronautical engineer. He said, "I took 15 years to learn mathematics. I'm not asking you to do that. I'm asking you to spend the next 5 years to learn mathematics." So he himself spent 15 years, but he says, "I'm not asking you to do that, what I did. I'm asking you to spend the next 5 years to learn mathematics." And I listened to him. And I'm glad I listened to him. I spent quite some time to learn mathematics. And I have the same thing to you, to suggest to you. Spend some time. If you learn mathematics, that one subject very well, you will find that everything else is very, very simple. Everything else is very simple. So I exhort, I request you, and join you to learn mathematics properly and consult. There are no exams. Now that you have no exams to pass, you have finished your exams, there are no exams to, you can afford to learn. You can learn the right way. Don't read stupid types of books. Read books that gives you conceptual understanding of books. There are many good books which gives emphasis on conceptual understanding, not to solve problems coming from the university exam. Okay, here I'll stop here for a few minutes. If you have some questions to ask. Abhilasha, I'll stop here for 2 minutes.
Abhilasha, can you try to see whether you can, Abhilasha, can you try if you can get the full screen mode in the view part, if you can take the view portion, just try to see if you can get full screen mode.
Okay, miss.
Then perhaps, yeah, it is better. See, it's better.
Okay. So participants, you can ask questions, post in the chat box, or you can even unmute and ask questions.
I have a public apology to make to KBM sir. He asked me for the diagrams. Now I noticed that whatever diagrams I have are already with him. These are the diagrams that I had, sir. I'm very sorry, I forgot.
That's okay.
Really
that's okay.
But I see
that's
that they're there now.
The proverbial absent-minded professor.
And I got involved in other things. Okay, I got involved in an FDP offered by. In fact, I'm sorry that I'll have to leave at 3 o'clock for that FDP. I hope I'll be able to hear a little more. It's like old times, sir. Listening to you, it's like old times.
My participants, please pardon my taking undue liberties with Professor Dr. Sudha Balagopal. She was our student, so I take liberties. She was our student. Although
yeah, that's an honor, sir. That's an honor.
I did not have the pleasure of giving her in the classroom lectures, but still, I consider her as my student in an extended sense. So,
I have attended almost all of the sessions that you have given to Vidya, sir. Any session that you have given, I have tried to attend. And I've made those notes also, and I'm preserving them. I don't know till when, but still I'm preserving them.
Okay.
I think there's a question for you.
Yes, sir. There's a question from Mr. Santosh Kumar. Sir, can you explain the mechanism behind cutting-edge trends to reduce vibration propagation?
That's over, Abhilasha. That's over. The next question is 0 degree freedom system under equilibrium. Yeah.
These are very unusual problems. There's a not only that 0 degree freedom system. 0 degree freedom system means it's a rigid body movement sort of thing. There is no vibratory motion. It's only the movement is only just a rigid body. There is an interesting book by two Russian books, and then he is talking about 1.5 degrees of freedom systems. So some interesting problems. So these are interesting questions, and they cannot be discussed quickly, convincingly enough. And nowadays, another thing has happened. You have first derivative, second derivative, third derivative, etc. You have fractional derivatives, 1.5 degrees system. First derivative, second derivative, third derivative, etc. What is meant by 1.5 derivative? D raised to 1.5 y divided by d t raised to 1.5. So these are fractional differential equations, etc. So you have fractional calculus. These things have come into being relatively recently. It has been suggested for quite some time, but now recently this has been applied to vibration problems, etc. So I would suggest some of you to take up these areas. If we have more time, then we can discuss some of the things. So the classical book, there are so many good books on vibration theory. I think the first thing, the book to be written in English language is by Timoshenko. Timoshenko was a Ukrainian, and he rose. In those days, what happened in Russia, the teachers, as a young teacher, most of the things used to happen in Europe. Germany and France. It used to be in France, and then a little later, the scene moved more to Germany. So in 1700 something, it was more in France and less in Germany. And then over a period of from 1700 to 1800, the scene moved, the center of gravity moved from France to Germany. They have different academic systems. They have France, France and Germany, they are neighbors, they have their professional rivalry, etc. German professors, you say, if they have classes in the morning and afternoon, when do they have the time to study? But then they used to make fun. German teachers make fun of French people. They said, if they have classes morning and afternoon, when do the students have time to study? But we know that both French and German systems have produced some of the most outstanding scientists. In France, in the Eiffel Tower, the 72 names, the names are written in gold letters. And these students were either students or teachers or both of the famous École Polytechnique. So there's nothing wrong with the French system. There's nothing wrong with German system. They are different. That's okay. Anyway, so the young Timoshenko went to Germany. And then first year he went to A. Foppel and Foppel brothers. And he worked with them. Then he went to the name eludes my family. Then he took some problems, and it was in those days he collected these interesting problems, and these problems later were the problems in his book Engineering Mechanics by Timoshenko and Young. So he used to do all these. So it is necessary to do that. If you do not do that, if you do not visit places where there is academic activity, you will miss out. So when I was young, I'll tell you my story. When I was young, we did not have a computer here. So I used to go to computation to industrial science, not industrial science, I used to go to Kolaba, technical teacher. Sudha, what is the name of that? TIFR.
TIFR, Tata Institute of Fundamental Research. Yeah.
So, beautiful lunch, hot, beautiful lunch. I remember Kolaba is beautiful, the institute overlooking the sea. And so I think it is necessary to go and see these places, because then only you get inspiration. The Tata Institute of Fundamental Research, they're doing wonderful work. So it is necessary to visit different places, Cambridge University, Oxford University, MIT, Stanford, Berkeley, whatever, these places. And they give you a lot of inspiration. When I turned back, I got inspired by visiting these places, Cambridge and MIT and Harvard and places like that. Anyway, I was fortunate. Not everyone will be probably as fortunate as I was, but you can surely see good institutes in India. Within India, there are very good institutes. You can go to visit some IITs and Indonesia Science, and there are so many good institutes. Spend some time and see what it's like, and recharge if possible. You can go abroad also. Nowadays, it is not as expensive as it used to be. So it's a good idea to go and spend 2 or 3 months, half fun, half business, and you will not regret this. You will see how other institutes work, and you will find that this style of working, the traditional way in which we have been, is not the right way of doing it. But so I'm trying to coax my youngsters to go and visit places where good academic work is being done. Okay, back to business. Now, multi-degree freedom system. I'm sorry, continuous freedom system. Please see if some of the slides, please. And just again, another one. Yes, that's it. So this is a beam. Oh no, the previous one. Yes. So this is supposed to be a beam, and the beam is a continuous parameter. See, the formula is a lumped parameter system. That means the mass is actually distributed throughout, but we pretend that the mass is located only at these locations. So that's called a lumping. So really the mass is distributed all along. And we pretend that half of this, 1/3 is, of the mass is here. So it's a lumped, all the mass is concentrated at one point, nothing at all in between. Then all the mass here, nothing at all, like that. So that's a lumped parameter. The parameter which is really, the mass which is really distributed, we pretend that it is not so. Why? Because if it is lumped, if it is continuous parameter system, the differential equation will be a partial differential equation. And then you find that the partial differential equations are not as easy to solve. So there are problems, there are difficulties. So you can simplify the problem by pretending that all the mass is considered at these points, separated by massless beams, etc. So as n goes infinity more and more, there are more masses, then it becomes a continuously distributed system. So you will find that now we will have a continuous parameter system. So I'm just giving on the right hand side of this beam is a cross section. So in the equilibrium position, you have a rectangular part. When it vibrates, what happens is this cross section rotates. You see, look at that line AB, or I cannot read it. That cross section line rotates. You see, rotates. So as a beam vibrates up and down, it not only vibrates up and down, it also rotates. Look at the cross section. Now the cross section, which was straight vertical, now has turned to the left. When it vibrates down below the equilibrium position, it will turn to the other side. So the cross sections do not remain straight and vertical. It rotates to the left and to the right. So it means there is some amount of rotation. So associated with this rotation, there is some energy. So you have to take into account all these factors. So if you do that, you will find that the equations of equilibrium are not easy to find out. So forget about solving. First, you have to talk about setting up the equation. How do we set up the equations? Setting up the equation itself is not easy. The traditional way of using Newton's law, etc., will not work here. So you use what is known as Hamilton's principle. I have written here Hamilton's principle in a very simple form. Delta of T1 to T2, T minus V dt equal to 0. What does that mean? T is a total kinetic energy. V is a total potential energy, but it is a good idea not to call it potential energy, call it potential, for reasons that I do not have the time to discuss. Don't get into the habit of writing potential energy. Use the word potential. There's a good reason. T is a potential energy, V is a kinetic energy. Now, this is for a simple case. This is a case for where there is a conservative system, where there is no damping, etc. Now, I told you we can neglect damping. Why do you want to neglect damping? Because if you include damping, what happens is the equations will become messy. They will become very complicated. And you don't gain anything, because we have seen that the damped natural frequency are almost the same as the undamped natural frequency. So why get into trouble? Why do you want so much of algebraic difficulties to get pretty much the same answer? So you neglect damping altogether and pretend that this is a conservative system. Conservative means this is a system in which energy is conserved. No energy is lost. No energy is dissipated. Otherwise, the Hamilton's principle is written as T plus W equal to T plus W dt equal to 0. This is the language of the calculus of variations. The Hamilton's principle is a calculus of variations. Some people say that, why do you want to learn calculus variation now? So that I can understand Hamilton's principle properly. I once saw a very old man. He was learning Sanskrit the hard way. Why do you want to learn this stage Sanskrit? so that I can read Kalidasa in the original. Oh, fair enough. So another person reading calculus variation. Why do you want to learn calculus variation at this old age? So that I can understand Hamilton's principle, the original. I can understand it properly. Hamilton was an Irish mathematician. He was such a brilliant person. He was so good that he became a professor when he was still an undergraduate student. Can you imagine that? Hamilton was so good that he was appointed as a professor when he was still an undergraduate student. Absolutely brilliant stuff. But the unfortunate thing is that as a human being, his life was a failure. He drank too much, had all kinds of unhappy affairs with girls and things like that. A very, very unhappy person. So his personal life was a misery. So I'm saying this because in our Indian tradition, the best learned men are also the finest examples of human beings. Say Shankaracharya, said to be the Sarvajna. He's also an extreme example of the finest human being. We used to give a lot of importance to human values. Unfortunately, now in India, we have lost that. Learned scholars are seen to be very, very mean, nasty, dirty people as human beings. So that's not fair. And it's time that we regain our lost glory. And I request you, I think there is somewhere there is some, we need to have a good personal life. Life was pure, personal, no motives, no cheating, and etc. etc. Look at the people. You know, two people got the Nobel Prize for the same experiment together, and one was slowly nudged out. Is that fair? The work was by joint people, but I do not wish to say anything about famous people. There are very, very famous people. They are extremely bright, brilliant, but as human beings, they are miserable, hopeless. So we don't. Let's not have. Let's be good human beings. I think we should be primarily good human beings before we become good academicians. So I suggest to my young teachers to be good human beings. But anyway, Hamilton. Now, in contrast, look at Euler. Euler was a brilliant, most brilliant person. He was also a fine example of a human being. Very, very magnanimous, generous, always willing to give credit to others, very modest, self-effacing, and so on. Let us rather be Eulers. And then Euler and Bernoulli. Bernoulli were also very bright people, but they were very, very mean, hopeless as human beings. So let's not be Bernoulli. Let us rather be like Euler. It is said Euler calculated without any mental effort, like birds fly and men breathe. So Euler was a remarkable person. He's a remarkable mathematician, but even more remarkable as a human being. Wonderful. And I just say this because Euler is said to be the person who invented the calculus of variations. Calculus of variations is almost the same as is an extension of differential calculus. You know the maximum minimum problem of differential equation. You have similarly a similar problem to find out the calculus of maximum minimum of functionals. I do not have the time to tell you all this, but I just want to make sure that engineers must necessarily learn calculus of variations. We did not do that. Our academicians have been very, 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 very poor. They have not introduced this calculus of variations as part of engineering education. That's a pity. There are many, very important things, wonderful things which are my former student and now illustrious colleague, Dr. Sudha Balagopan, will tell you how important it is to have our, what is that? What is the name?
Calculus variation?
No, no.
For control theory, yeah. Yeah. So we connect them to control theory. Unfortunately, control theory is
No.
not.
What is the name of the subject which you got a PhD? What is it?
It is in that. No, it was in game theory. Game
theory, yes. Concrete game theory. So it is necessary to learn these new things. Whatever. Let's come back to our problem. So here, what happens is when this moves up and down, y is the displacement. Y depends upon the x coordinate and also time coordinate. So y equal to y x t. X and t are the independent variables. Y is a dependent variable. So we say y equal to y of xt. Now what is velocity? Velocity of a particle. So of a particle means at the point x is fixed. X is fixed and you have to find out the derivative of y with respect to t, keeping x constant. What does it mean? That is a partial dy by dt partial. So please show the next equations, please, Abhilasha.
Yes, sir.
Can you make it? Yeah, that's fine. Look at that kinetic energy calculation. Translation and velocity dy by dt is a velocity of. Where is it? Yeah. So now slope is dy by dt at a fixed time. T is constant. So what is the rate of change of slope? This is d by dx of d2y by dx. Now what is the total kinetic energy? Total kinetic energy is half into mass into velocity squared. Half mv squared. So that's, and what is this one? This is a kinetic energy associated with the rotation of the cross section. You see the cross section rotates. The slope changes. You see, the slope changes, and that's how. So half of I. This is a polar. This is the polar moment of inertia. Half I omega squared. You see, what is half mv squared? Is the kinetic energy of translation. The kinetic energy of rotation is half I omega squared. So what is omega? Omega, these are the calculated. Total kinetic energy is T equal to half of the first half mv squared plus high. So now total potential energy, I think it is better to call it potential, not potential energy. So this is the, for a beam, civil engineers should have no difficulty in understanding this. Yeah, U half of EI into slope squared. Look at this, curvature squared. So this is a now potential energy of external potential of external external load. So this is the external load. This is the external load. So this is the potential. Oh, this is the potential. So the total potential is V. This is the potential is T. So you have Rayleigh's Hamilton's principle, which is delta of this. Oh, this is the T minus V dt, and it requires some manipulation, which is a little difficult. So next slide, please. Next, so simpler mathematics. So yeah, so you get finally what happens is this is the differential equation. This is the differential equation of motion. To do that, you have to go through all these, and it is a little too difficult for those who have not learned calculus of variation, and it's not possible to teach you calculus of variation in 5 minutes or 10 minutes. So when you believe me, I've gone through all this, and this is the equation, and this is the differential equation of motion. And in the simple cases, some of the things are neglected, then becomes a simple problem here. If the force, there is no external force, the right hand side becomes 0, and then you have this equation. So that's a wave equation, and this differential equation is to be solved. How do you solve them? Generally, these equations are all very difficult to solve, so you need to have approximate solutions. how do you get approximate solutions? There are several methods of obtaining approximate solutions, and we need one or the other of these approximate methods. What's wrong with the analytical solution? Nothing wrong, fine. But analytic solutions are not easy; they are difficult. So when you solve this kind of equation, these are vibration problems. They are partial differential equations are of three kinds: the elliptic, hyperbolic, parabolic. So you have like b squared minus 4ac, like b squared minus 4ac. B squared minus 4ac is 0. You see, ax squared plus bx plus c equal to 0. So b squared minus 4ac, the two roots are minus b plus n minus root of b squared minus 4ac by 2a. And if b squared minus 4ac is 0, then the roots are positive. I mean, they are real. Otherwise, complex conjugate, etc., etc. So in exactly the same way, partial differential equation also you have the coefficients a, b, c, and then depending on the nature of b squared minus 4ac, the partial differential equations also can be classified into parabolic equations, elliptic equations, hyperbolic equations. These wave equations are all hyperbolic equations, and the methods that work very well for hyperbolic equations will not work for may not work for other things. So that is necessary. So when you work with approximate methods, it is necessary to know something about vibration theory and the mathematics, the nature of the partial differential equation. Otherwise, we will not be able to use proper methods for the proper equations. So, but I will forget about this. I have not done these calculations because the approximate methods themselves are a huge ocean, and then there are so many approximate methods, and each has some advantages, disadvantages, etc., etc., etc. So all that cannot be packed into one. So that's it. Now we can have some discussion if you like. We'll stop. In any case, I will stop here for some time, and then we'll see how we can proceed further.
Yes, sir. Yeah. Our discussion is still okay, sir.
You have some questions to ask, or somebody wants to add something, we'll talk about that. Okay, sir. Yes, sir. One question is there. Can I ask now, sir? You can, yes, sure. In fact, it doesn't have to be an question. Somebody can make some statements also about your opinion, or whether you agree or whether you have some. You can have comments also. You're not necessarily question. They're all teachers, so they're all they're not traditional students. They're teachers, so they can add something, or you can question or whatever. Don't accept. Yes, sir. Both teachers and few students are also there. MTech students, structural engineering students are also there. They also can ask. They also can add. Yes, sir. One question is from Mr. Kamal Kishore. Good afternoon. In India, problem traffic-induced vibration increase day by day. How can we reduce? What is that? What's it again? What's it again? In India, problem traffic-induced vibration increased day by day. So how we can reduce it? That is the question. What is the first sentence? There are vibration-induced problems. Yes, the traffic. Traffic-induced vibration, sir. Traffic-induced vibration. Yes. Yeah. So what type of vibration of what? What is the system? Traffic on a passenger car? Passenger car?
I think he's talking about the acoustic problem. There's a lot of sound issues as also other kinds of issues.
No, vibration is, although vibration and acoustics go together to some extent, acoustic problems are different. Here, acoustic
perhaps on the bridges, on the roads, etc.
Yes, bridges, yes. There are, that depends on the nature of problem. There are some problems. I think we saw there is a relatively recently built bridge across the Thames, and I think that Professor Datta had talk to us about this bridge. And on the first day itself, it was closed because it was subject to vibration. What happens is, if it's a suspension bridge, the suspension bridge will have oscillations. So when an army marches on this, generally they have left, right, etc. If by a bad choice, if this frequency happens to coincide with the natural frequencies, one of the natural frequencies of the suspension bridge will start oscillating, and the oscillation will become will build up, and the structure may come down. That's why when an army is march along the suspension bridge, they are advised to fall out of step, out of synchronism. They should not left, right, like a disciplined set of people. They should not want like that. And the suspension, there are different types of problems. In fact, in 1940s, before 1940s, civil engineers never used to learn vibration theory. But then on a sad day in 1940, the huge Tacoma Bridge in Washington, not Washington DC, Washington State, got into a violent flutter, broke into pieces, and fell into the water. What was happening was that this bridge, there is a slight breeze blowing across this. Now you see a breeze is a load. When there is a load, you see civil engineers know that if there is a load, the beam deflects. And when the beam deflects, unless the load is acting through the shear center, you know that deflection is associated with bending also. A beam will not only, when the beam deflects, there will be also an associated twisting unless the load passes through the shear center. And the shear center is often not on the beam, but outside on the cross section. Sometimes it happens. If it's a channel section, etc., you know the shear center is not on the column, on the channel outside. So because of these reasons, this there's a breeze which was blowing across. And it so happened that there's a negative damping. The damping was negative. What does it mean? Energy is not dissipated, but energy is sucked into the system. The breeze that blows across was supplying the energy needed, and this energy is sucked into the system. And when energy is sucked into the system, how does it manifest? It can manifest only in the form of increased vibrations. If I have a lot of money, how does it manifest? I'll probably go in a Rolls-Royce car or Benz car or whatever. So an increased, a lot of money, extra money will show up. Maybe I will have gold ornaments all over the place, and Benz car, etc., etc., etc. So, and how does money manifest in me as increased spending? So how does energy into a system manifest itself in a vibrating system? Only in the form of increased vibrations. So you find that the Tacoma Bridge got into a violent flutter. That's and it was the amplitude of vibration was phenomenal. I have seen the film of this, and it is terrifying. You get the feeling that all hell has broken loose. It's terrifying. It's really terrifying. And this got the violent flutter. The whole thing was uprooted. It broke into pieces. Fell in there. Then the civil engineers. It became necessary for civil engineers also to learn vibration theory, structural dynamics, etc., became important. In our country, structural dynamics did not really become part of our curriculum. I think only in postgraduate classes they teach, but I think it's necessary to learn vibration theory for all students. Civil engineers definitely. So now, as far as traffic is concerned, when the traffic, there's a noise associated with traffic. It is not an easy problem. It is when an ordinary bus, car, etc., noise is not that much of a problem. But when a train moves, then the roaring of trains, that becomes a problem. These are very special problems. Roaring of a train, etc., is a problem in itself. It has its own special mechanism. If we had more time, we would have indicated some idea. But on a car, if the car goes on a rough road, then what happens is there will be vibration. So you see, the passenger will not have comfort. The back of the head, there's a place called medulla oblongata or something, the seat of consciousness. That part should not be subjected to too much of vibration. So we must make sure that, imagine that somebody is sitting on the car. We must make sure that even when the tires, wheels move up and down, the suspension must be so designed that the passenger, the head of the passenger is not subjected to too much of vibration. There is another problem also. You may have delicate instruments which may have to be shipped from one place to another in a truck or something. So even if the truck goes on a rough road, the vibration must be such that the vibration should be contained. The electronic instruments should not be damaged. So in other words, the electronic instruments should not have too much of acceleration. Then the electronic instruments will damage. So you have a problem. So that is why you have the stochastic problems and all this. There are a different type of analysis, a different type of mathematics is needed for that. So when there are uncertainties, why uncertainties? Because you have the same car, same driver, same road conditions as far as possible. Still, if you take the vibration measurement, it will not be the same. So you find that whatever is within the control of the experimenter is kept the same. The output, the displacement versus time output will not be the same. So in other words, even if you measure, whatever you measure is not the input, is not the output, is only one of the several outputs that you could have had. So then, therefore, you have to use advanced statistics, stochastic theory. So you need a different type of mathematics to discuss the vibration associated with traffic, etc. So the suspension system in a car must be designed so that it can, even if the road is rough, the passenger can still have a nice time. That is it. I'm sorry, I will not be able to give you much more than that. What else can I talk about? Shall we have a 2-minute, 3-minute break? Let's have.
Yes, sir.
Abhilasha?
Yes,
can
sir.
We have
Sure, sir.
2 or 3 minutes?
No, sir. After winding up our first session, we'll start our second session by 2:45, sir. We shall have 15 minutes break, sir.
Okay.
So it is 2:30 now. We shall have a break for now. If there is no further questions, if there are questions, we shall just ask and clear it now. Otherwise, we shall break for 15 minutes and be joined by 2:45, sir. Participants, is there any doubts or any questions?
Abhilasha, can I suggest something?
Yes, sir. Yes, ma'am.
I suppose you understand that KBM sir requires rest from time to time.
No, I don't need any rest.
It's better that way, sir. Why don't you give your voice a little rest?
No.
Okay.
It is easy to talk.
So let them collect their questions and keep. Is that better? So in this next session, they can ask the same questions. Because you won't have any trouble.
It is easy to talk, but it is difficult to listen.
Okay. Are you using something for your ears?
After 15 minutes, we'll wait.
Yeah.
Let them have some relaxation.
Tea and relaxation and questions, collection of questions, preparation of questions.
Yes, sir. Yeah.
So Abhilasha, I'm really sorry that I will not be able to attend the next version because I have a meeting.
Okay, ma'am, no problem.
That also is a civil engineering kind of thing, construction, construction. Okay, the Council for Construction of India.
Okay. Okay.
So they are giving an FDP, which I thought that you people should attend. Unfortunately, I'm the only person who's attending from. But I'm collecting the details and I'll be passing them to you especially. Okay, that's the trenchless technologies that I've talked about.
Yeah.
You should have some work there. Okay. Okay, then thanks a lot. In fact, I enjoyed joining your FDP. Okay, thank you.
Thank you so much, ma'am. We are honored. Thank you, ma'am.
I think it's a very nice kind of topic. I think it's of interest to everyone because I can also add a few things. Like for instance, we learn many of these things as a part of control theory. But of course, it's again. Then he was talking about the vehicle going over a road. We can talk about the conveyor belt conveying things. Okay, there again, the torque pulsations give rise to problems. So similar kinds of problems are there in all areas. And so it's good to have I wish that there were some other engineering branches, faculty members attending. Then it would be nice to have discussions, okay, some comparisons, etc. Okay, I hope did you inform all the teachers in the class in the institute, our college?
Yes, ma'am, but we can have only 30% of participants, in-house participants.
Yeah, but people like me can attend, doesn't it?
Anyone can attend, but as per ATEL, we have this rules.
Yeah, that's okay. I will not be, and I don't.
You can always attend, no problem.
So I'll use that welcome, okay, whenever I can. Okay, thank you.
Thanks certificate and all.
No, I don't want a certificate. I can't. I don't think I have time to use the certificate. Okay, anyway, it was nice being here.
Okay? Thank you so much for this.
Thank you. Thanks a lot. I do thank everyone here. Okay, bye-bye.
Okay, thank you, ma'am.
Thank you. Bye-bye.
Participants, we shall rejoin after a small break because it is hectic today, I know, because we started from 9 o'clock. Along with 3 sessions, we had our inaugural session also today. So take rest for 15 minutes and we'll rejoin by 2:45. So from tomorrow, we'll be having time from 9 to 4 itself and 3 sessions per day like that. Okay, only today it is too much hectic because of 3 sessions and inaugural session. Okay, so all of you can rejoin by 2:45 and third session is by our KBM sir itself. So feedback link will be shared after last session, third session. Okay, we'll be having only one feedback session. Feedback link to be filled today after this. It is combined of second and third session. Okay, so no feedback link for present session. Together we'll give it at the end of next session. Okay, so all of you can leave and get refreshed and come back after 15 minutes.
Hello?
Yes, sir. Yes, sir.
Yes. Yes, I'm ready. They are ready. I'm ready.
Okay, sir. Okay.
Okay.
Okay, sir. Okay. Should I change the slide, sir?
We don't need any slides now.
Okay, sir.
I'll just talk about maybe the calculus thing we can set up. Calculus.
Okay. Okay, sir.
Set up that. I will not need it, but I'll just see. Oh, yes. Yes, next slide. Next slide. Next slide. I don't think we don't need it now. I'll just yes, just before that, the previous one. So I thought I will give you a short introduction to Hamilton's principle. Let's leave that. Before that, let's see how you solve a problem. Abhilash, I think we'll close this. We'll listen to this later. We will listen to this later. Now,
Okay.
Let's say you have a vibration problem. Let's say there's a fan which makes too much of noise. What do? Imagine that you have a fan which makes too much of noise, and because it is too noisy, nobody is buying that fan. So the company runs into losses, and the manager calls you, and they said, we are not able to, our fan doesn't sell because it's too noisy. Please examine this and do whatever is needed. What kind of thoughts will go through your mind? So let me raise this question. Participants, please answer if possible. Here is a fan, let's say a ceiling fan, which makes too much of noise, and therefore nobody buys this, and the company running losses. So you're asked, you're an engineer, you're asked to identify the problem and solve the problem. This is the problem that comes to you. What kind of thoughts will go through your mind? Let's wait for 2 or 3 minutes. Think about this and see how you respond. And we will try to see how you approach such a problem. Somebody? Don't hesitate to give answers. The answers may be wrong, downright stupid. It doesn't really matter. Doesn't matter. So,
sir, one answer is, sir, from Mrs. Shipa Rachel, that is change the coil.
Yes, the fan makes too much of noise and you're asked to solve this problem. What kind of thoughts will go through your mind? How do you do that? How do you approach this?
From Vatsala, to reduce the noise from the fan.
What do you do? Now, let me try to, let's say, convert some of the young teachers to my way of thinking. Let's have some open-ended questions. Here is a bridge, a railway bridge is suspected to be dangerous. Examine. What kind of thoughts will go through your mind? Similarly, we are not discussing beam vibrations. I think we'll some other day, if there is an occasion, we will discuss that also. But now, for the time being, let's come back to our problem. Now, what kind of thoughts will go through your mind? How do you do? Now, don't hesitate to make wrong answers. Nobody is so smart that he can get to the right answer quickly in a shot. Nobody, not even Timoshenko or Den Hartog. Nobody is so smart that he can get at the reason just on shot, just like that. So don't hesitate to make mistakes or even blunders. Doesn't matter.
Yes, sir. Answer from Arya Sudhir, solve motor issue. Then from Chris and John's, lubricant. Use lubricant. Use lubricant, sir.
Yes, normally in table fans, you use the bearings that are used are ball bearings. In ball bearings, lubricants is generally, grease is the lubricant. But you have lubricant grease only if you know that it is a reason. So how do you suspect that this is because of lack of lubrication? What makes you suspect that this is a? Please, one or two participants, please make some comments, make some answer, give some answer. Let the answers be wrong, doesn't matter.
Yes, sir, I am reading out the questions from the chat box, sir. I am reading out the questions. I mean, reading answers from the chat box from the participant sides. That is one participant said that it is lubricant. More answers, please.
I think our own young teachers, probably Vidya teachers, can probably make some suggestion, and then so if you say change the bearings, if you say change the bearings, how do you know that it is a bearing that is a villain? It is just like saying you go to a doctor and say, I have some complaint. Okay, remove the kidneys. But how did doctor know that the kidney is a villain? Without knowing that, what's the point in removing kidneys? Without diagnosing properly. So there's no point in changing the bearing unless you know there is a bearing. That's a villain. So the point is, we do not really know. Everybody is equal, right from Timoshenko and Den Hartog to all of us. They're all the same boat. We do not know the reason. But what is the systematic way of going about to try to find out the reason? The way to is, from our experience, we know that it is some resonant condition which may be giving rise to noise. What could be the noise? How do you know that? No. The first thing to be, almost the first thing to be done is to measure the vibration frequency. So for the noise, let's measure the speed of this. Speed is. How do we do? When the fan rotates, we use a stroboscope and measure the speed. Let's say the speed is 120 RPM. What is the frequency? What is the frequency? 120 RPM is corresponds to so many. 120 RPM is corresponds to 2 revolutions per second. 2 revolutions per second means 2 into 2 pi, which is 4 pi. So many hertz. So you measure this and you find that it is 120 RPM, and then check and realize that the speed, the frequency corresponding to that is 120 RPM. So which means 2 RPS revolutions per second. That corresponds to 4 pi radians per second, which means about 12.5, something like that, 12.2, 12.3 hertz. Now, 12.3 hertz. Do you have any, what kind of frequency, what is that frequency? Is it a natural frequency or is it a operational frequency, external frequency? What is it? Now, what kind of frequency? Now you see the fan has 3 blades or 3 blades, let's say. So every time it hits the air stream, it gives some noise. next blade. So if there are 3 blades, then the frequency will probably be 12.2 into 3, 36.3. Does it give us some clue? Think about that. And how do you measure the speed of a fan? By stroboscope. That is the easiest way of. What is that? Just flash a light and then change the frequency, and then you see, it appears to stop. That's the stroboscope effect. Then you measure the frequency. I think if you have not used it, you must make sure that you do use stroboscope and see how you do that. Now you can see that the motion of the if you adjust the speed, you will find that the motion of the fan can be arrested. So it is like this. The fan will appear to be stationary if you flash light at the stroboscopic frequency, and then if it has a torsional vibration, you will see that the whole thing rotates, and as it rotates, each leaf swings back and forth. So you can see this is the naked eye, provided the overall motion is arrested. And the overall motion can be arrested by using what is known as a motion analyzer. That is basically it's a stroboscope, motion analyzer. So the entire rotation is arrested. It is actually rotating, but because of the stroboscope, you see it appears to stand stationary. And then in the stationary thing, the fan moves and back and forth slowly. So you can see that it's a torsional oscillations. Now that's one way. So now the first requirement is almost the first thing that you do is to diagnose the vibration problem is measure the frequency. When I say measure the frequency, it is not one frequency. There are generally several frequencies. A pure sinusoid exists only in classrooms and examination halls. In life, there is no pure sinusoid. Along with the basic sinusoid, there will be undesirable but unavoidable harmonics. So you have several harmonics, several frequencies. So if you have a predominant frequency, the primary or the fundamental frequency, and then several other frequencies. So you want to know what frequencies are contained in a signal. That is known as a spectrum. So you have to get the spectrum of the vibration. Whether it's a table which is vibrating, whether it's a floor that is vibrating, whether it is a fan that rotates or whatever. Whatever you do, almost the first thing that you need is to get a spectrum. Spectrum means what frequencies are contained and how much. It is almost the same as a Fourier analysis, except that it is a Fourier analysis is valid only when a periodic phenomenon is concerned. This may not be a periodic phenomenon, so it is not Fourier series, but it is somewhat similar to that. So it's like this. Along with the signal, there are also undesirable but unavoidable high frequencies. So noise is generally, the general characteristic is the amplitude is small, but the frequency is large. It is something like 2 sine t plus 0.01 sine 50t. So 0.01 sine 50t is the noise, and the other one is a signal. So how do you get rid of the noise? So can you avoid the noise? How do you analyze the noise? It is something like this. You have a tap water and well water. Both are mixed together. How do you remove the well water out of it? It's not easy. So similarly, when you get a signal in an electric wire, that signal contains the original harmonic or original signal and harmonics. Noise, the signal and the noise. How do we deal with them? So the first thing that you understand is, let's see, you have 2 sine t plus 0.01 sine 100t or 50t. What will happen if you put it through an integrated, if you differentiating circuit? If you do it in a differentiating circuit, what will you get? Your 2 sine t will become minus 2 cos t. The other thing will become 0.01 into 100 cos t. So you find that the noise has taken over. It becomes more. Now imagine what will happen if the signal is put through an integrator. What will happen? 1 will remain 1 itself. 0.01 will now get reduced by 0.01 divided by 50, which is very, very small. So one technique to get rid of noise is to put the signal through an integrating circuit. If you do that, what will happen? The noise is gone. The noise becomes very, very small. So one way to deal with noise in these things is to put the signal through an integrating circuit, and then you will get rid of them. Now, what about the remaining thing? There are several frequencies. Let's say 2 sine omega t plus 0.72 sine 3 omega t, etc., etc. So how do you know this? So what you do is you have an instrument, something like an equivalent of a Fourier series. If the expression is known analytically, we can integrate and find out. But here is a vibration signal that's not given in an analytic form. You do not have the mathematical expression. You cannot differentiate it or anything because it's not given in a functional form. So what do? You have to do this experimentally. So you put the signature put the signal through a FFT analyzer, fast Fourier transform analyzer, FFT analyzer. What does it do? It gives us what frequencies are contained and at what amplitudes. This information is given to us. Once we know this information, then and then only we can start diagnosing. It's just like you go to a doctor and they say, I have some complaints. The doctor doesn't do anything. Simply he gives you, okay, you remove your kidney or remove your liver or something. It's stupid. So let us do a systematic way by which proper diagnosis can be done. So when you get the vibration, first get a signal. How do you get a signal? This table is vibrating. I want to get a signature, the signal. How do you do that? Put an accelerometer on this. What's an accelerometer? It gives us a signal, an electrical signal. It gives us a voltage proportional to the acceleration of this. Why acceleration? Because measuring the acceleration and measuring the velocity and displacement involves integration. If you integrate, then you will find the noises are all gone. If you try to measure the displacement and get the velocity by differentiating, the noise becomes worse. So what you do is, let's say this floor is vibrating. I want to know how to solve this problem. So what do? I will get a signal of this vibration. And how do I do that? I will choose an accelerometer and measure the signal. The signal changes with time. How will you do that? You put an accelerometer and measure the vibration signal, and then put it through an FFT analyzer. What does it do? It tells us what frequencies are contained and how much. That's what it does. So now how do you choose the accelerometer? There are several types of accelerometers. So you have to decide how to choose this instruments. But this becomes a more specialized sort of thing, vibration measurements, and it's a subject in itself. And without getting some introduction to that, we will not be in a position to choose the correct the correct accelerometer for a given purpose. It is something like this. if you want to measure the force, what force, what type of UTM can we use? What should be the capacity? We must know the capacity, etc. We must know. If you do not know, you would not be able to do that. What is the current? You can use an ammeter, but what is the range? What kind of current are you expecting? Is it in the form of micro ampere, milliampere, or ampere, or heavy currents? Without knowing that, you cannot use an ammeter. So if you say choose an ammeter, that does not solve the problem. We must say the range, etc. So if you say with an accelerometer, you measure the signal. What does it give us? It gives us the acceleration of the vibration. If you integrate it once, twice, you will get the displacement time. If you put it through an FFT analyzer, it tells us what frequencies are contained and where. Once you get this, you will get some idea of what the problem is. Now, returning to our fan, do you have an offending frequency at 2 hertz? 120 RPM, that is 2 hertz, 12 point something hertz. No. There are three blades. So 3 into the thing. Every time is a blade giving one push. No, it's not so. Then what is it? Again, I put it measure this and then use an FFT analyzer. Is there any clear sinusoid? No, there is no clear sinusoid. So what does it mean? It shows that the bearing is not at fault. If it is a bearing, what will happen? After it completes one revolution, it will make a. So then if the bearing is at fault, if it is rubbing the bearing on one side, once in every revolution, whenever it comes over, it makes a noise. So the noise, therefore, will have a frequency equal to the frequency of rotation. Then, if that is the case, run it at a different speed. Run it at a different speed, say 180. Now, 180 revolutions means 3 revolutions per second, which means 3 into 2 pi. 2 pi is 18 point something. So from 12 point thing, does it become 18 point something? Yes, it does. Now you are more or less sure that yes, it is a bearing which is at fault. Like that. Suppose you find there is no predominant, no clear sinusoid. You are only all kinds of frequencies. Then you know that what is the conclusion? What is the conclusion? The conclusion is that this is not because of any bearing problem or anything. It is not because of any fault in the bearing or anything like that. It is because of the turbulence in the airstream. And therefore, the correct solution is not to change the bearings, not to change the leaf, not to change nothing. But the flow of air on the blade is not proper. That's because of too much of turbulence. Therefore, what is the correction? The correction must be the blade angles are proper, not proper. So the blade shape, the shape of the blade is to be changed. The blades are to be redesigned so that the flow of air on the blades is not as rough as it is now. So you'll find that now the correction is there's no point in changing the bearings or anything like that. No use. That will not help. What you should do is you must make sure that the flow of the air is less turbulent. It is a turbulence which causes noise. So therefore, the blade shape geometry must be used. The best thing will be to use fluid simulation, and then you can get the better angles, etc. So that's the correct way. Let me stop here. Did you understand, participants? Did you understand this example? Abhilasha?
Yes, sir. Yeah. Yes, sir. Clear, sir.
Did I make myself clear?
Yes, sir. Sure, sir. Participants,
Will you
please
ask
answer.
somebody to ask some questions or make some comments or something? Then I will just take up something else.
Yes, sir. Participants, please reply, sir.
Huh?
If there is some questions or points, I shall read out, sir.
Comments, or just say if you have you understood. If you understood, that's fine. That's fine too. That's fine. Did you understand the way you approach the problem?
Yes, sir. Participants are saying yes. Yes, sir. Yeah.
No, let us have a similar problem, which is about a railway bridge is suspected to be dangerous. How do we approach the problem? Civil engineers should be comfortable or not comfortable. We really do not know. We may make mistakes. Who does not make mistakes? Only one who doesn't try at all. He's the only one who doesn't make mistakes. Let's not hesitate to make mistakes. How do we approach? I don't know either. Nobody knows this. But I will try to tell you if there is some mistake. I will try to point out. And in suggesting that, I may make another mistake. Somebody else must point out. You give me an answer. There may be some mistake. I point out the mistake. In pointing out the mistake, I myself may introduce 2 other mistakes. Somebody else will point them out. And then after a discussion among 3 or 4 people, we'll come to, oh yeah, this is possible. So how do we do that? Let's think about that. Okay. Now, this is the way you try to, when a vibration problem is reported, this is how you begin your investigation. Almost always, you must measure the frequency of the signal. What frequencies, and then you decide, are these frequencies related to something? For example, if there is a noise, you say, my neighbor is using a, what is it called? Chuck, what is it called? A pile driving. So that may be causing the vibration here. How do I know that? You can check whether you have the same vibration when the fellow stops his work and goes away at night. Probably there's nothing. But he does, that bang, you're driving a pile. That could be the reason. I don't know. So how do I check? I measure the vibration here, measure the frequency here, measure the frequency there. You can see the measure. And if they are related, then you can see that, oh, yeah, probably that is the one which is causing. So like that, you have to think about this. So nobody can come to the right answer the first shot. So think about this. Let's take this example of a suspected railway bridge. And what kind of thoughts will you go through? Will you order that all trains should be stopped? That would be a serious matter. Train service is completely. After all, you are only suspected. You have not. You don't know for sure. The problem is the railway bridge is suspected to be damaged. So what kind of? How do you go about doing this? This is not my job is not to discuss this problem, although I would have loved to do that. But I keep this as an open question because most of you are of civil engineering background. Sooner or later, or you may have already taught strength of materials or structural engineering or whatever. So just think about this. I think we must change from our, we have written the same type of questions, a beam, so many meters, this load 2 kilometers. From exam to exam, it is exactly the same story. The span may change. One thing is simply supported, the other is fixed, this kind of stuff. But if one of the same thing, it's the same story. That should change. And then let us have an open-ended question and try to see how you can think. In most problems, as they occur to engineers, will not come in that form. For example, somebody may say, your old uncle will say, my nephew is an engineering student. He's a bright fellow. Let's say he has got a lot of marks. Let me ask, what type of pump do I need I have a coconut grow. I want to send water. What type of pump is suitable? So what type of pump will be used? That is how it is. In other words, the definition of the problem, this is the client specification of the problem. From the client specification, we must give the technical specification. What is the technical specification? What is height? So where is what is the level of water in the well? How much of water do you want to do, etc. So from the client specification, we must learn to give a technical specification, head, discharge, time, all these things, etc. So let's reorient our approach to engineering problems by asking some open-ended questions and trying to willing to make mistakes, and in doing so we will have some exposure to how thinking must be done. So you see, the kind of questions that we have on the university examiners have no clue at all. There's no resemblance at all to the kind of questions that we get when we work as engineers. You have no clue. It makes so a machine. The machine was working here. It sunk into. It was raining, and then the wheels went down by ½ meter. What do we do? So this kind of question. So how do we handle this? What type of question is that? So let's have some kind of open-ended questions and try to see what kind of how do you justify this? Let's say your vehicle. That vehicle, it is raining like hell, and then it went down. The tires maybe ½ meter down. You are in trouble now. You cannot drive this way. So what do we do? So you let us pretend they are not. There are no theory or integration or differential equations or anything like this. Differential equations may come later. But first, let us, from the client specification, let us learn to define, give the technical specifications. And then the right way of approaching. First, we must be willing to accept that nobody is so smart that you can get to the correct answer first shot. We will make mistakes. Let's not hesitate. And when you do that, you will have a certain amount of what shall I say, humility. Other people think that I have got very high marks. They think that Justin or Abhilasha or Nabu report is a very, very bright person. We may have got some marks, all right. Third form, I may have got 100 marks in history. What does it matter? It has no relevance now. So, but that has nothing to do with, we have no idea at all of, so we are just babies. We are babies in the woods. We have no clue at all. So with a certain amount of humility, I don't know. I studied for so many years, and other people thought that I was a bright student. But irrespective of what other people, I know nothing at all. So with that humility, let us approach this. Let us learn, try to ask questions. Don't be afraid to make mistakes. Don't be afraid to say stupid things. That's fine. So let's say, so shall I leave this problem at this stage and think of something else, experimental methods or something other. shall I stop here and wait for some response? Justin, can you hear me? Can you hear me? Justin?
Yes,
Can
sir.
you
Yes,
hear me?
sir.
You can hear.
Yes, yes. Yeah, I can
Do
hear
you have some?
Yes.
Do you have some suggestions for me?
Yeah, actually, I have classes now. Just now it rejoined. So that's why I don't have continuity so far. So let me see.
Okay. Abhilasha, do you have any suggestions for me?
Yes, sir. Going well. We are really thrilled to hear from you after a long time.
So
All this.
I would suggest like this. To the young teachers, I would suggest like this. First, go to some industries and see construction. Say a cement mixing. Simple. It doesn't have to be a very complicated thing. And try to see how you do that. And then you'll have a lot of other questions. What questions? How do you see whether there's too much of water, etc. So what's cement ratio? What is the role of that? Ask simple questions and try to see. Don't say you finish the experiment and then be eager to get back home. That's not the idea. That's not the way. So try to see how a construction, a structure is erected, steel structure, how a steel structure is erected. How do you do that? So let's see and try to get into that industry mode so that you know you can ask the right questions. How do I do that? What is meant by you just in a classroom, you say simply supported. The beam is simply supported. What is meant by simply supported? How is it done in practice? Simply supported means knife edge. You don't buy a knife and put it there. So what is meant by fixed end? How do you get that? What is the way by which it is done? So see a bridge. Next time you go to get down there and then see how each part is supported and what is the way by which, etc. That way you will see how, in practical life, what you see is very different from what you see in the classroom. The classroom is it's a very, very simplified sort of thing for analysis. But before the analysis, we must have a fair idea of the problem. Unless you understand the problem, there is no further point in making analysis. So don't do the analysis first, then becomes pointless. What kind of, now why do we, you see when a problem is presented like that, you don't see any differentiation or integration or anything like this. So you get the feeling, what the hell am I doing it? Why the hell do I learn differential equations? I don't see any need. Sure, the problem is not solve this differential equation. There is no engineering problem like that. But what does it do? I want to get greater heat treatment. I want to make this harder. How do I do that? It's not sufficiently hard. I need to, I want to get greater hardness for this steel piece. How do I do that? So I'll do this. I'll heat it up to this and cool it. How fast should I cool? What is a cooling medium? Do you want me to cool slowly? So what does it mean? If it means cooling slowly, what is the consequence? So if you take the steel to beyond the recrystallization temperature, etc., and then cool it, if you cool slowly, what will happen? If you cool fast, what happens? So you have to know the metallurgy of this. With the metallurgy, so first, it doesn't seem to be a metallurgical problem. I want to harden this. Yes. So what is the temperature? How fast should I cool this? I want the hardness to reach halfway on the rod. So if you want to solve this, you will find that if you want to solve this problem at a fundamental level, then you will find that it calls for this heat transfer analysis. So it becomes a one-dimensional heat transfer analysis. Then you need your differential equations, and then you need etc., etc. Then you need how so. So you say, is it you cool water for 2 seconds, 3 seconds? We don't know. So you say T. You just leave it at T, and then don't say there was 3 seconds. And then later, depending on what you want, you can put T equal to 2 or T equal to 3 or T equal to 4, and for the same solution, you can get different possibilities. So like that, you From a raw point of view, from the raw statement of the problem, you try to have a technical understanding of the real process. And then if the process is to be analyzed systematically, carefully, scientifically, so that for different various combinations, various cases, you don't have to solve this again and again and again. You solve once and that's it. And then you put different numbers, you get different numbers. And then you get then the other questions. How do you measure hardness? These associated questions come up. So if you say this is not hard enough, this is hard. So what kind of hardness? When you think of measuring hardness, then you find there are problems. It is not just one hardness. There are so many types of hardnesses, which is relevant here. So you are forced to ask these questions. So engineering is not about answering questions. It's about asking questions. Ask the right questions. And then once you get asked the right questions, then you will get slowly the idea of it. So unfortunately, you cannot do that because you have limited time, so many, the syllabus is to be completed, examinations will be asked on this kind of thing, etc., etc. So there are problems of this kind. So at least when these, I would say that if these participants, by the time these participants become senior and will reach a decision-making stage, please make sure that these kind of stupid, day-to-day, highly predictable type of problems are not asked again and again and again. It's the same beam problem. It is 3 meters, it will be 4 meters. It is 5 kilometer, it is 7 kilometers. Otherwise, it's all the same. Find out the reflection or something. It's one thing. Why? What the heck? Why do you want to find out the reflection? Let's learn to ask these questions. Why do you want to ask these questions? Why do you want to find out reflection? How to find out is one question, but before that, how to find out reflection is one thing. Analytically, how will you find out reflection? Experimentally, how will you find out reflection? Why? What are the problems, etc. So, but why do you want, before you do how, let's learn, why do you want to measure deflection? What is the point? What does it matter whether the beam deflects by 2 millimeters or 2.5 millimeters? What does it matter to me or to anybody else? So what could be the answer for this? Your participants, will you try to answer this question? We ask, calculate the reflection. Why do you want to calculate reflections? What is the use? What does it matter whether it is 2.2 millimeters or 3.5 millimeters? What does it matter to me? Now you see, in a statically indeterminate structure, small displacements can lead to very large forces. So whether the reflection is, especially when there are, statically indeterminate structures, the deflection calculation is very crucial because small displacements will result in very large forces. So therefore, it is important. So let's answer less. Let's ask more questions. Even if you don't answer, that's fine. Let's ask some questions and then try to see how it can be done. So I will tell you some books. If you want to learn vibration theory, the first book on vibration theory is by Den Hartog in English, because when Timoshenko left, he was a Ukrainian. He used to go to Germany and then learn these things with senior professors there. That's how he became very good. Then the revolution broke out, and he lost. This young Timoshenko had done so much a problem. For the first time, they decided that promotion should be based on academic merit, not about seniority or age. Then young Timoshenko became professor at a very young age. But then soon the revolution broke out, and then he had no job. He lost his job. So he survived giving tuition in physics, chemistry, mathematics, etc. And then he had to run for his life. fortunately, in a train, one of his students was the person. So he was happy to help his old teacher. And later turned out that that is the last train to leave what later became USSR, etc., etc. So he moved over to Croatia, where he found that they are following the book written by Timoshenko himself, where he spent 2 or 3 years, beautiful years. And then from here, he heard that there's a new country which is coming up, the United States, land of opportunities. So young Timoshenko moved over to, first he went to Michigan, and then later he went to, he's the one who introduced the summer school. Yeah. And so many interesting stories. So this is the first book. And then he did not get a job there first. He joined Westinghouse Electric Company, industry. He was not there. There are many engineers. So young Timoshenko, well, it's not, he was not very young, but Timoshenko taught young engineers the various basic things. He gave the first lectures. It is these lectures which later became vibration problems in engineering. And one of his students was Den Hartog. He wrote a book. He was also an engineer in Westinghouse Electric Company. So he became. So there are some of these stories are very inspiring. If you know the stories that without inspiration you cannot do any work. Otherwise you will curse. You will curse the strength of materials. You curse Timoshenko. You curse everybody, and then okay, help with that, and then you write something. That will not help. So technically, you can say I'm interested only in engineering. I'm not interested in the authors. It doesn't work like that. So you can say technically, I'm interested only in my sister. I don't care about her husband. I don't care about her family. This is true in theory, but it doesn't work like that. If you're interested in your sister, you must be interested in her family, husband, etc., etc. So if you're interested in strength of materials, you must be interested in the people who created the theory. How life and the work, the consequences, stories, interesting stories, all these things, and they inspire. And you need to read books like that, and make sure that you don't read silly books written by people who have not enjoyed. Read books only written by masters, written by people who have enjoyed. Only a person who is happy will be able to make others happy. So read others. Don't read books by teachers who are very, very frustrated because they don't get their salary, they don't get a promotion, they don't get their leave, etc., etc. Then they get naturally frustrated. Go to people who have enjoyed, who enjoy life, and then learning is not at variance with enjoyment. Learn to learn, read, enjoy, etc., etc. That will be a very nice way of doing it. In fact, we used to do this working holiday. My friend Devdas Manan and another person also, 3 of us, we had done a considerable amount of work, but we had not written the paper. Because when you stay in your place, there will be some other things. If you stay at home, there will be some little things here and there. The bulb, electricity bill is to be paid, the bulb is used, and the gas is over. You have all strains. But we went to the place, Cape Comorin. We in the Vivekananda Center. We stayed there. Very, very nominal rent, practically nothing at all. We enjoy Cape Comorin and the sea and the moon and everything. And then you sit in the room and then just, 4 days we wrote, all the data was there. We wrote 3 papers in 4 days. So that's a working holiday. And you can take your spouses also, let's say women. Let them have some fun. Let them go there and have some shopping or some a few thousand. Give them some 3,000 rupees, 5,000 rupees or something. Let them enjoy while we do our work, etc. So that I suggest that we can introduce a scheme of working holiday. Just enjoy, and enjoyment is not at variance with learning properly. So I'm saying a few general things. If there are some specific questions, and do you? Is there anything specific that I can tell them?
Sir, some questions are there in the chat box. I'll ask at the end of the session. Last, sir. Some questions are there in the chat box, sir.
Ah, yeah.
Yeah. So after you stop your presentation, we'll discuss that.
Okay. What is that? What are the questions?
Sir, first question is by Mr. Santosh Kumar. That is, sir, is tensegrity free of vibration?
1 minute. It got it disappeared. So let me.
Sir.
Oh yeah.
Can
yeah.
you,
Yes.
Yeah,
I got it. What is the question?
Okay.
What is the question?
Is tensegrity free of vibration, sir? Question is tensegrity free of vibration?
If, what is that?
Tensegrity free of vibration. Is tensegrity free of vibration? That is the question asked, sir.
Can I have it on the screen? I'm not able to catch the word.
Are you able to see the chat box? And the chat box you can see, sir.
Where is that chat box?
In the last
yeah.
chat. You can take chat. Yeah. So last question, that is, by Mr. Santosh Kumar.
What is the question?
Sir, is tensegrity free of
What is that?
vibration?
What is that word? Tensegrity means what? What is that? I don't know the word.
Mr. Santosh Kumar, you can switch on your mic and ask the question.
I don't know what the word is. I don't know what the word is. Tensegrity means what? I don't know.
Are you there, Mr. Santosh Kumar? Please switch on your mic and here.
So, it's a. I do not know. I'm sorry. I do not know structures. I'm not a structural engineer. I'm a mechanical engineer. Yeah.
Another question. Any other questions? You can type down the chat box, or you can even switch on your mic and ask question directly. The question is given to all.
I hope that all of them have had some exposure to vibration. I hope they're all civil engineers or
Yes, sir.
engineers?
Yeah, civil engineers, structural engineers, most of them. From geotechnical is also there.
No.
Other stream also. Mainly structural engineers, sir.
It's a lovely subject. Structural engineering is a lovely subject.
Any other questions?
Do you think Abhilasha, do you think I must actually teach in the way in which we teach in a classroom? No, not necessary.
Sir, this is a perfect way, sir. We are listening to you. Very much interesting way, sir. You are taking class.
Okay. Show me the first slide, calculus slide, and just say a few things. Calculus.
Should I share it, sir?
Yeah, I'll show you some. I have prepared something, but I thought it may be too difficult for them, so I'll give the calculus slide. Yes.
Okay, sir.
Next slide. Next slide. Yes, this is a vibration system, single degree freedom system. You know that there is no damping, so it's a conservative system. There are only kinetic energy T equal to half into m. All the mass is at the mass. Spring is without it. The spring has no mass, and the mass has no elasticity. That is known as a system. Yes. So this is called a discrete system. Really speaking, everything has mass, and where is the spring? The spring is not a physical spring. The spring is a representation it's a representation of the springiness or elasticity. There are two things, mass and elasticity. These are the two things which are crucial for vibration. So I'm trying to give you an introduction to Hamilton's principle. So here is, for this system, simple system, kinetic energy T is half into mx squared. Remember, x is not a constant. X equal to xt. T changes. I'm sorry, with time, the body moves up and down. So x changes as a function of time. So xt is x as a function of time. So half into velocity squared. Velocity is what is x dot? M into x dot. I think it's x. It must be x dot. Velocity is x dot. Dx by dt is velocity. So half into m into x dot. It's too small. I cannot see this. But I hope it's, yeah. If you enlarge it, you can see half into m into x dot. X dot is velocity. So half into m into v squared is a velocity. Potential energy, it's better to call it potential. Half into k into x squared. K is spring. The extension is x. So the spring force is the spring force is gradually extended. So half into k into x dot x squared is a potential energy. Now let us write Hamilton's principle. Next slide. Yes, this is the Hamilton's principle is T minus V dt is to be stationary, is to be maximum or minimum or stationary where the tangent is horizontal. So what is a function x equal to xt that makes the above integral stationary? This is the question. So this is a question in the calculus of variations. So from here, I want to make sure, what does this mean? This is stationary. Stationary means its first variation is 0. It's something like you stay on the horizontal tangent. Maximum, you draw a tangent, it's horizontal. At the minimum, you stay on a horizontal. Now, first maximum and then going up, down. So there's a tangent is horizontal. At the point you draw a tangent, and the tangent is horizontal. What does it mean? On the tangent, as you walk along the tangent, you neither go up nor go down. Use stationary. So what is a function x equal to xt that makes the above integral stationary? This is the question. To answer this question, you need the calculus of variation. I'll just give you some simple. Next slide. Next slide. Next slide. Analogy. Maximum functions, similarity, necessary condition, sufficient condition, maximum. Just like a differential calculus, you have next line. Next line. This is a function. What the x so mapping from x to y equal to x squared. From y, it's a mapping from the set of functions to a set of functions. So this is the input, output, and this is the function. This is known as domain, this is known as index. So mapping from the set of numbers to a set of numbers. Example, y equal to x squared. If x is given, y can be calculated. The maximum minimum problem of the ordinary calculus is posed as, what is the value of x that makes y a maximum or minimum? Now you have the same thing here. Y of x of t, y input, it's a function. So it's a function. The input itself is a function, and the output also is a function. Last time it's a number. Input is a number, output is a number. This time input itself is a function, output also is a function. So this is a domain of continuous functions. This is a range of continuous functions. Whatever. The question is an example. I equal to integral a to b f x y y dashed. X is the independent variable, y is the unknown function, y equal to yx, y dashed is dy by dx. So if y equal to yx is given, if y is equal to yx is given, this can be calculated. The maximum minimum problem of calculus of variation is, what is the function y equal to x? What makes I a maximum or a minimum or a maximum. So next slide, please. Oh. Yes. So this is the question. What is the necessary condition for this to be maximum minimum? So let's imagine that this is the actual minimizing curve. Let's imagine that this this firm curve is the actual maximizing curve, which is not known to us. If it is known to us, there's nothing to calculate. There's nothing to calculate. So to this maximizing function which exists but is unknown to us, you add a variation eta x, and then you multiply it by some number and add to this, vary the function y. Next slide, please. Next slide. So y equal to yx is the actual extremizing curve. It is not known in the beginning. What is shown is only a representation of the extremum. If this is an arbitrary admissible function, and then to this unknown function, you add various combinations of various ratios of eta x. So you have a family of curves. Among these admissible functions, what is the correct value? The correct value of epsilon is 0. Why? Because yx is the actual maximizing curve, although it's not known to us. So eta x is chosen by us. For what value of epsilon will you get the correct one from this family of curves? Eta equal to 0. Because eta equal to 0 gives us from this family. For this family means for various values of eta equal to 0.1, 0.2, 0.3, etc. So various, which is the correct one? The correct one is the one which gives eta equal to 0. So now from here, next among them. So when you do this, you see this I. You change this x to, you vary this. This is a language which is, what happens is for various values of, this becomes for different values of epsilon, this becomes different values of epsilon. So you see, if epsilon is 0.1, you will get one value. Epsilon is 0.2, you get another value. So the whole thing becomes a function of epsilon. Now various values of I epsilon. What is the maximum value? The maximum value is I. The maximum value. So here is a function. I is a function of epsilon. What is the maximum condition? What is the necessary condition for the maximum? Di divided by equal to 0. So this is the necessary condition when epsilon equal to 0. When epsilon equal to 0, this gives us that. So this is the problem in differential calculus. You see how Euler has converted the calculus of variation problem into a differential calculus problem. See this, how this. Next slide. Yes. So I am just integrating. I am carrying out the integration. If I integrate this, you get. This is what you get. I hope. Now you see that this is what you get. The calculus variation problem is converted to an ordinary differential calculus. I want to calculate this and set it equal to 0 and epsilon equal to 0. So this is differentiating inside the integral. So you can take it inside, first differentiate and then integrate. That's possible. You can do that. If you do that, you will get this like this. Now, eta. What happened? It's disappeared. Screen disappeared. The screen disappeared.
Sir, I think it is, sir. No. Yes. Is there any connection problem over there, sir?
It doesn't matter. It doesn't matter. So from this may be probably a little too tough, particularly in online class where I cannot see anything, I cannot draw anything.
I think there is no connectivity problem here, sir. Maybe the.
So what happens is from here you get the condition. Can you say the screen? The screen is lost.
Okay, sir. Okay, sir. Let me do it once again. Let me see.
Give me. Yes.
Are you able to see now, sir?
Yeah, I got it. So
okay.
now, this is Euler, was a very clever man. Euler converted the problem of calculus of variations into a differential calculus problem. So he calculates that. Next slide, please. Next slide, please. So he does that and leave eta as it is, and eta dash must be converted to eta. So differentiate this by parts. So if you do that, you get the yes. If you differentiate this part, next slide, please. Next slide. Yeah, yes. So this is left. You integrate by parts. So first function into integral of second minus integral of differential of the first into integral of second. So you get that. So you get this. You see how clever he is. Eta at 0 at x1 is 0, eta at x2 is 0. So this term is out. Integrate terms are 0. So you have only this. And this must be true for all values of eta. And therefore, the necessary condition is this. This is the famous Euler equation. This is the Euler's equation. This is the necessary condition. The sufficient conditions are harder. We will not go into that. So this is df by dy minus d by dx of df by equal to 0. This is the Euler's equation. You apply this to our Hamilton's principle, and if you do that, I have done it. Next slide. Next slide. Next slide. Next slide. Next slide. Next slide. Hamilton's principle. Hamilton. Yes. Yeah. So look at this. This is Hamilton's principle. This is the Euler equation which you have derived. Now here you see. Look at that. The independent variable here is x. The independent variable here is t. So where you have x, you must write it as t. And where you must. So you see, this is the equation. So you write. So the same thing in this Euler's equation. X is the independent variable. Here, t is the independent variable. So where there is x, d by dx, it must be. If you do that, this is what you get. This is what you get. So if you apply this, you get Hamilton's principle. You get the equation of motion mx2 dot plus kx equal to 0. Now, in the general thing, next slide. Next slide. You calculate the yes. You see, independent variable x. Now it is t. Unknown function y, here it is unknown function is x. The function is f, the function here is L. And f of x, y, z becomes L of t, tx, a dot. So Euler equation becomes, if you make these changes, this is the Euler equation. This is the Euler Lagrange. This is known as the Lagrange's equation of motion. What is Lagrange's equation of motion? Lagrange's equation of motion is the Euler equation of variational calculus when Hamilton's principle is expressed as a variational problem. What did I say? I said once more. This is this is Lagrange's equation of motion. Lagrange's equation of motion is the Euler equation of variational calculus when Hamilton's principle is expressed as a variational problem. Once more, the third and last time, this is a Euler's equation. Euler's equation of motion, Euler's equation of dynamics, Euler's equation of motion is the Euler equation of calculus variations when Hamilton's principle is expressed as a variational problem. If you do that, you will get the answer. And this is a method which is used to calculate the equation of motion for the beam problem. That's how it is not easy. If you are seeing it for the first time, I do not know how some of you may be seeing it for the first time. I think I was surprised. You know, I told you that I taught in Germany for 2 semesters to international students. There they teach this stuff in the 3rd semester undergraduate. 3rd semester undergraduate. What are we talking about? So I gave them some problems based on this, etc., etc. 3rd semester students. What the heck? What are we talking about? And then you feel uneasy. I do not know how you feel uneasy. You see, look at this kind of funny sort of things when you're seeing all these things for the first time. When I saw it for the first time, I saw this for the first time only when I was in Kharagpur IIT. I had never seen this earlier undergraduate students. What's a shame? We just somehow, it is the syllabus, etc., are set up by people who have never seen this, nor have they any desire to see this. So it is set up by some kind of old people who have lost their academic interest or who never had any, and then you say it is too advanced. What are you talking about? Where the rest of the world teaches at the undergraduate level, here we don't even teach even at the postgraduate level. What now? What are we talking about? Anyway, whatever. When I saw it for the first time, I felt uneasy. And I expect that some of you, if you are seeing it for the first time, some of you may feel uneasy. Well, you have to see this. So if you apply this Hamilton's principle, then you can get the equation of motion easily. No, Newton's law is okay. Newton's law is fine for simple problems. But Newton's law is not valid in an accelerating frame of reference. If it's a case of a double pendulum, one pendulum hanging on the above the other pendulum, you cannot use Newton's law because the point is it is valid only in an accelerating, in an inertial frame of reference. Whereas an accelerating frame of reference, it's not valid. So what do? So you have to use Hamilton's principle. You have no other choice. So simple problems maybe you may think that it's difficult, but complicated problems are no more complicated, whereas Newton's law cannot be used at all. Anyway, and the other advantage is that you see, both T and V are scalar quantities. Whereas if you use Newton's law, etc., the equations of motion are all vectors. They use vectors. And you know, everybody who has used vectors knows that vectors are not easy to deal with. Our educators have made sure that vectors are also not taught. Undergraduate students do not work in terms of vectors. What a shame. So, but those who have worked with vectors will know that vectors are harder to deal with than scalars. Here, there are scalars. T and V are both scalars. So they're easier to deal with. So you have no problems. So the difficult problems are easier. The simpler problems are difficult, but more difficult problems are simpler. And if you use this, it is in good shape to use everything. And there are very interesting things. Some of you're all structural engineers. You would have studied plate theory. You know the plate theory. The basic fundamental equation is the biharmonic equation. Biharmonic equation. That equation, there are a lot of problems. When it is, people did not know how to write things properly. The plate equation became. There are more boundary conditions. You see, on a free plate, what are the conditions? The bending moment is 0, the shear force is 0, the twisting moment is 0, and there are 4 boundary conditions, but the differential equation can take only 2 boundary conditions. So what do we do? Now, these problems are very difficult. You cannot answer them unless this problem is a plate theory is formulated as a variation problem. Then all these things come up very, very easily. They come out very, very easily. So if you have not studied this, please be sure to learn theory of plates and shells using variational notation and variational calculus, etc. And then you will get the correct equation nicely and easily without any problem. So S.S. Rao, he was in Kanpur IIT. Now he is in the United States somewhere. So I also ventured to write a book on variational problems in engineering, and I would request you to see this, read this. It's not an easy book. It is not at a textbook level. It is at a higher level, and not only just for inexperienced teachers. It is meant for people who know things well and who want to know things very, 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 very well. So it's not going to be easy. It'll be tough, but it's worth. And you can see tough books. I think I have a feeling that if you read this book, you do not have to record many other books. Yeah, otherwise, to learn calculus and variations, it will take a long time. You may not be able to do this very easily. Although it is a mathematical book, I have included enough mathematics in this problem also. I would request you. To know general vibration, S.S. Rao's book is very good. There are so many books, good books, but I recommend S.S. Rao, a very good, knowledgeable person. Okay, shall I? I do not know how far I was effective. Probably not. Look at this. I have written here. Lagrange's equation of motion, which is Euler's equation of variation. This was a variation problem. And boundary conditions are harder. So shall I stop here at this stage and hope that you will, I shall be happy to answer if you have some questions to ask, or comments to make. You can contact me at the email or by telephone number also. And Abhilasha, can you circulate to them by email address and WhatsApp number? So
okay. Surely we'll circulate this PPT, your notes, and also we'll circulate to the participants.
I feel sorry. I feel sorry because if you're getting out of bed and just listening to this, probably will not understand much. But what else? I don't know. Anyway, so I thought they must be given an orientation, at least, or introduction or initiation to variation calculus, some tough material. Okay, then.
Participants can have questions now.
Oh yeah, sure. I have nothing else to do.
So some questions are there in the chat box. I shall read it out, sir. So first question is,
classical plate theory. Plate theory is simple. Plate theory is classical. Plate theory is the same. But then there are now there are more difficult plate theory. They are difficult. They are. I think I would suggest that you read Reddy's book. Jane Reddy's book. Jane Reddy is an outstanding person. If you do not know, if you are not familiar with him, I think it is necessary to be familiar with him. He is a outstanding. He's a great scholar, Jane Reddy, and anything that he writes is very good. He will not write nonsense. Is a Jane Reddy's book. So there are plate theory. There are Von Karman theory of plates. Von Karman. I think this is another thing. When I was your age, I got my degree and my friends, I got good marks, good grades. What stupid? I had never heard Timoshenko's name, Von Karman's name. What kind of degree is that? So anyway, so there are Von Karman theory of plates, etc. They're tough. They're not easy. But so if you learn, I think you have to learn all these things properly. What happens when the theory of plates, large deflection, what happens, etc., etc. And I also feel that this style of plate theory is not proper. You have to learn it as part of applied mechanics or part of engineering mechanics. The traditional type of plate is not okay. There is bending in both directions. It's all fine, but there is more to it. Anyway, the Timoshenko's book is good, although it contains only. Plate theory is very good, but it does not give the advanced theory, Von Karman theory of plates, etc. It doesn't give, but it's very good for that level. But shell theory is not sufficient. Timoshenko's book on theory of plates and shells. Plate theory is very comprehensive, although it does not contain new things. But shell theory is quite inadequate. It's not sufficient at all. If you want to read, Golden Visor is the right book. But if that is not possible, at least our what is William Fluge's book, at least Fluge shells minimum Fluge's right thing is the Russian books. That's, okay. I'm not able to hear you.
Sorry, sir.
You have muted?
Yeah, sir. Yeah. There is one more question from Anmita Sinha. That is how to model chimney.
How to?
Model chimney. Chimney, sir.
Chimney. Yeah. They are difficult. That depends on what are the factors. Do you want to talk about tall buildings? Do you want to what is the type of loading? Do you want to talk about thermal loading only, or just are there blast loading, wind loading, etc.? What is the nature of wind loading? You do not know wind loading. You do not know in what direction the wind will decide to wind. So there are uncertainties. When you have uncertainties, then there is a different technique of doing this. You need stochastic theory, etc., etc. It's difficult theory.
Sir, she's asking about thermal and wind load. Thermal loading and wind.
That 1 minute video, please.
Okay, sir. Okay.
Please 1 minute video.
See? Just a minute, sir.
1 minute. Only 1 minute. Okay. That is a stone crusher that I had told you about. Yeah, this is the one on the left, the white shirt is a speaker. The one with the red, the other one, the black pants, was my former student. He was my client. Okay. You can close this. Now you see, for those who are not familiar with this industrial scene, you see that the whole machine, etc. Who will suspect that this is the crucial part of it is the differential equation, etc. Where is the differential equation there? You don't see a differential equation, and the crucial part is writing a differential equation and vibration isolation. Who will know this? That's why people say that I don't see any differential equation. No, true. You don't see any differential equation. If you write a differential equation on a piece of paper and paste it there, it will not solve the problem, will it? It will not. So the equation is there in the background. And I think many people make sarcastic remarks that all this is unnecessary. Let a person who has done well, professionally competent person, let a competent person say that this is not necessary. Again, people who have not learned anything, saying that this is not necessary. What sanctity does it have? Let's get hold of a person like Dr. Devdas Menon of Madras IIT. Let him say it is useless. Then I'll buy that argument. Not the people who have no idea at all and then say this is unnecessary. Differential equations are unnecessary. Why? Because I don't see any differential equation in the industry. True, you don't see. So that's why. People who have no idea at all, who have done extremely badly, they're telling us that differential equations are not necessary. It doesn't carry any conviction. Let people who have succeeded very well, let them say that's not necessary. Then yes, I'll buy that. Okay, then.
Any other doubts? If you have got anything to ask, you can use your mic and ask questions. We have got 15 more minutes. Any questions or doubts from participant side?
So I'll end this with a word of apology. I'm sorry that this has not become fully effective, perhaps. I wish we had eye contact and discussion person to person. Even then, they're difficult. I did not plan to teach it from step by step, etc. Because there is no point. Because there are people with different backgrounds. I doubt whether it is possible for people to understand in the sense that they will be able to reproduce this, etc., etc. That's not necessary. But I think if you have got some idea of some exposure, there are things to be learned, etc. That's all that I had in mind. I think that's all that's realistic. Anyway.
If we don't have any doubts, we shall wind up now.
Yeah.
So thanks a lot, dear KBM sir. Actually, vibration theory is a topic which most students and teachers are afraid of, as it contains a lots of equations and derivations and all. But actually, you explained it very simple way and interesting way with lots of day-to-day examples and also case studies from different parts of the world also. Also, the interest shown by you to study more and more. Actually, we all must emulate it from you, sir.
If there are no travel restrictions and you give me some time, then I promise to teach you properly, in the sense that you will learn properly. But there should not be a time condition restraint, because it is difficult to some stories and some general things, etc. That I think we have got the wrong idea that only if you are able to study from an examination point of view, only that kind of study is good. Even that requires some revision, rethinking.
Thank you so much, sir. Thank you. Definitely we'll see again.
You're welcome. I do not know, irrespective of what the listeners think, I, for one, enjoyed talking to them, whether or not they understood or whether or not they liked it. I enjoyed talking to you, and I thank you, Abhilasha, and I hope that we will meet sometime. When the corona restrictions are over, I hope we will meet in person. And
sure. Yes, sir. Sure, sir. Definitely.
So, bye until then. All the best.
Thank you, sir. Thank you. Thank you so much, sir. So participants, I shall share the feedback link. One announcement is that if you have not joined our WhatsApp group, please join there so that I can share the further details and all there also. So please join WhatsApp group also. Okay.
Oh, he says, Professor Vivekananda has some kind words. We thank you for the kind words. Okay then.
Okay, thank you, sir. Yeah, thank you.
Yeah. Bye until we meet again.
Yeah, yes, sir. Thank you. Sure, we'll meet soon. So participants, tomorrow our sessions are from 9 o'clock, 9 to 4 o'clock. Okay. So join 5 minutes before 9. That is by 8:55 a.m. All of you please join tomorrow. We are having 3 sessions tomorrow. Okay. So thank you all. I shall just a minute. I shall share the feedback link now. Here itself I'll share, and also in the WhatsApp group. Okay. Okay, so this link, that is the feedback and attendance link for the last 2 sessions. That is session by Dr. KPM Tripathi sir. Okay, 2 sessions. You have to write the MCQ also. You have to attend all the questions also. Okay. Is it not able to access? Okay, okay. Just a minute, I will check once again. Okay. Please check now. Okay. Please submit within 30 minutes. Now it's a follow-up, you can submit it. Just a few minutes only needed, right? So please submit now itself. I think it is okay for someone, but is it asking permission? Yes or no? Maybe because you have joined using some other mail ID. Please use the mail ID which you have used. Okay, still it is not. Okay, I will check it and clear it and share in the WhatsApp group. Okay. Okay, sure, sir. And check it and resend it in the WhatsApp group. Okay. So shall give some more time. We'll clear it and submit very soon. Okay. I hope everyone is there in the WhatsApp group. Shall share it over there. Okay. Yes, can leave now. See you all tomorrow at 9 o'clock. Thank you. Thank you all. Stay safe. Take care too.